Science is a rigorous, systematic endeavor that builds and organizes knowledge in the form of testable explanations and predictions about the world. 1. 2. Modern science is typically divided into three major branches. Frowny face. 3. Natural sciences, example, biology, chemistry, and physics, which study the physical world. The social sciences, example, economics, psychology, and sociology, which study individuals and societies. Wink with a frown. 4. 5. And the formal sciences, example, logic, mathematics, and theoretical computer science, which study formal systems, governed by axioms and rules. 6. 7. There is disagreement whether the formal sciences are science disciplines. 8. 9. 10. Because they do not rely on empirical evidence. 11. 9. Applied sciences are disciplines that use scientific knowledge for practical purposes, such as in engineering and medicine. 12. 13. 14. The history of scientific discipline spans the majority of the historical record, with the earliest written records of identifiable predecessors to modern science dating to Bronze Age Egypt and Mesopotamia from around 3000 to 1200 BCE. Their contributions to mathematics, astronomy, and medicine entered and shaped the Greek natural philosophy of classical antiquity, whereby formal attempts were made to provide explanations of events in the physical world based on natural causes, while further advancements, including the introduction of the Hindu-Arabic numeral system, were made during the Golden Age of India. 15, 12, 16, 17, 18. Scientific research deteriorated in these regions after the fall of the Western Roman Empire. During the early Middle Ages, 400 to 1000 CE, but in the medieval Renaissances, Carolingian Renaissance, Etonian Renaissance and the Renaissance of the 12th century, scholarship flourished again. Some Greek manuscripts lost in Western Europe were preserved and expanded upon in the Middle East during the Islamic Golden Age, 19, and later by the efforts of Byzantine Greek scholars who brought Greek manuscripts from the dying Byzantine Empire to Western Europe in the Renaissance. The recovery and assimilation of Greek works and Islamic inquiries into Western Europe from the 10th to 13th century revived natural philosophy, 20, 21, which was later transformed by the scientific revolution that began in the 16th century, 22, as new ideas and discoveries departed from previous Greek conceptions and traditions, 23, 24. The scientific method soon played a greater role in knowledge creation, and it was not until the 19th century that many of the institutional and professional features of science began to take shape, 25, 26, along with the changing of natural philosophy to natural science. 27. New knowledge instance is advanced by research from scientists who are motivated by curiosity about the world and a desire to solve problems. 28, 29. Contemporary scientific research is highly collaborative and is usually done by teams in academic and research institutions. 30. Government agencies and companies. 31, 32. The practical impact of their work has led to the emergence of science policies that seek to influence the scientific enterprise by prioritizing the ethical and moral development of commercial products, armaments, healthcare, public infrastructure, and environmental protection. Etymology. Look up science in Wiktionary, the Free Dictionary. The word science has been used in Middle English since the 14th century in the sense of the state of knowing. The word was borrowed from the Anglo-Norman language as the suffix science, which was borrowed from the Latin word scientia, meaning knowledge, awareness, understanding. It is a noun derivative of the Latin sciences meaning knowing, and undisputedly derived from the Latin scio, the present participle scire, meaning to know. 33. There are many hypotheses for science's ultimate word origin. According to Michiel de Vaan, Dutch linguist and Indo-Europeanist, scio may have its origin in the Proto-Italic language as *skij or *skijo meaning to know, which may originate from Proto-Indo-European language as *skh1ie, *skh1io, meaning to incise. The Lexikon der Indo-Germanischen Verben proposed scio is a backformation of nesire, meaning to not know, be unfamiliar with, which may derive from Proto-Indo-European *skh in Latin secare, or *skh2- from *setu, I, meaning to cut. 34. In the past, science was a synonym for knowledge or study, in keeping with its Latin origin. A person who conducted scientific research was called a natural philosopher or man of science. 35. In 1834, William Whewell introduced the term scientist in a review of Mary Somerville's book on the connection of the physical sciences. 36. crediting it to some ingenious gentleman, possibly himself. 37. History. Main article, History of Science. Early history. Main article, History of Science in Early Cultures. Clay tablet with markings, 3 columns for numbers and 1 for ordinals. The Plimpton 322 tablet by the Babylonians records Pythagorean triples, written in about 1800 BCE. Science has no single origin. Rather, systematic methods emerged gradually over the course of tens of thousands of years, 38, 39, taking different forms around the world, and few details are known about the very earliest developments. Women likely played a central role in prehistoric science, 40, as did religious rituals, 41. Some scholars use the term protoscience to label activities in the past that resemble modern science in some but not all features. Wink with a frown. 42, 43, 44. However, this label has also been criticized as denigrating, 45, or too suggestive of presentism, thinking about those activities only in relation to modern categories, 46. Direct evidence for scientific processes becomes clearer with the advent of writing systems in early civilizations like ancient Egypt and Mesopotamia, creating the earliest written records in the history of science in around 3000 to 1200 BCE, 15, 12 to 15, 16. Although the words and concepts of science and nature were not part of the conceptual landscape at the time, the ancient Egyptians and Mesopotamians made contributions that would later find a place in Greek and medieval science. Mathematics, astronomy, and medicine, 47, 15, 12. From the 3rd millennium BCE, the ancient Egyptians developed a decimal numbering system, 48, solved practical problems using geometry, 49, and developed a calendar, 50. Their healing therapies involved drug treatments and the supernatural, such as prayers, incantations, and rituals, 15, 9. The ancient Mesopotamians used knowledge about the properties of various natural chemicals for manufacturing pottery, faience, glass, soap, metals, lime plaster, and waterproofing. 51. They studied animal physiology, anatomy, behavior, and astrology for divinatory purposes. 52. The Mesopotamians had an intense interest in medicine. 51. And the earliest medical prescriptions appeared in Sumerian during the 3rd dynasty of Ur. 53. They seem to study scientific subjects which have practical or religious applications and have little interest of satisfying curiosity. 51. In classical antiquity, there is no real ancient analogue of a modern scientist. Instead, well-educated, usually upper-class, and almost universally male individuals performed various investigations into nature whenever they could afford the time. 54. Before the invention or discovery of the concept of physis or nature by the pre-Socratic philosophers, the same words tend to be used to describe the natural way in which a plant grows, 55, and the way in which, for example, one tribe worships a particular god. For this reason, it is claimed that these men were the first philosophers in the strict sense and the first to clearly distinguish nature and convention. 56. The early Greek philosophers of the Milesian school, which was founded by Thales of Miletus and later continued by his successors Anaximander and Anaximenes, were the first to attempt to explain natural phenomena without relying on the supernatural. 57. The Pythagoreans developed a complex number philosophy. 58. 467 to 68 and contributed significantly to the development of mathematical science. 58. 465 The theory of atoms was developed by the Greek philosopher Leucippus and his student Democritus. 59, 60. Later, Epicurus would develop a full natural cosmology based on atomism, and would adopt a canon, ruler, standard, which established physical criteria or standards of scientific truth. 61. The Greek doctor Hippocrates established the tradition of systematic medical science. 62, 63, and is known as the father of medicine. 64. A turning point in the history of early philosophical science was Socrates' example of applying philosophy to the study of human matters, including human nature, the nature of political communities, and human knowledge itself. The Socratic method as documented by Plato's dialogues is a dialectic method of hypothesis elimination. Better hypotheses are found by steadily identifying and eliminating those that lead to contradictions. The Socratic method searches for general commonly held truths that shape beliefs and scrutinizes them for consistency. 65. Socrates criticized the older type of study of physics as too purely speculative and lacking in self-criticism. 66. Aristotle in the 4th century BCE created a systematic program of teleological philosophy. 67. In the 3rd century BCE, Greek astronomer Aristarchus of Samos was the first to propose a heliocentric model of the universe, with the Sun at the center and all the planets orbiting it. 68. Aristarchus's model was widely rejected because it was believed to violate the laws of physics. 68. While Ptolemy's Almagest, which contains a geocentric description of the solar system, was accepted through the early Renaissance instead. 69. 70. The inventor and mathematician Archimedes of Syracuse made major contributions to the beginnings of calculus. 71. Pliny the Elder was a Roman writer and polymath, who wrote the seminal Encyclopedia Natural History. 72. 73. 74. Positional notation for representing numbers likely emerged between the 3rd and 5th centuries CE along Indian trade routes. This numeral system made efficient arithmetic operations more accessible and would eventually become standard for mathematics worldwide. 75. Due to the collapse of the Western Roman Empire, the 5th century saw an intellectual decline and knowledge of Greek conceptions of the world deteriorated in Western Europe. 15. 194. During the period, Latin encyclopedists such as Isidore of Seville preserved the majority of general ancient knowledge. 76. In contrast, because the Byzantine Empire resisted attacks from invaders, they were able to preserve and improve prior learning. 15. 159. John Philoponus, a Byzantine scholar in the 500s, started to question Aristotle's teaching of physics, introducing the theory of impetus. 15. 307, 311, 363, 402. His criticism served as an inspiration to medieval scholars and Galileo Galilei, who extensively cited his works 10 centuries later. 15. 307 to 308, 77. During late antiquity and the early Middle Ages, natural phenomena were mainly examined via the Aristotelian approach. The approach includes Aristotle's 4 causes: material, formal, moving, and final cause. 78. Many Greek classical texts were preserved by the Byzantine Empire and Arabic translations were done by groups such as the Nestorians and the Monophysites. Under the Caliphate, these Arabic translations were later improved and developed by Arabic scientists. 79. By the 6th and 7th centuries, the neighboring Sassanid Empire established the Medical Academy of Gondoshaper, which is considered by Greek, Syriac, and Persian physicians as the most important medical center of the ancient world. 80. The House of Wisdom was established in Abbasid-era Baghdad, Iraq. 81, where the Islamic study of Aristotelianism flourished. 82, until the Mongol invasions in the 13th century. Ibn al-Haytham, better known as al-Hazan, began experimenting as a means to gain knowledge. 83, 84, and disproved Ptolemy's theory of vision. 85, Book I, 6.54. Page 372. Avicenna's compilation of the Canon of Medicine, a medical encyclopedia, is considered to be one of the most important publications in medicine and was used until the 18th century. 86. By the 11th century, most of Europe had become Christian. 15, 204. And in 1088, the University of Bologna emerged as the first university in Europe. 87. As such, demand for Latin translation of ancient and scientific texts grew. 15, 204. A major contributor to the Renaissance of the 12th century. Renaissance scholasticism in Western Europe flourished, with experiments done by observing, describing, and classifying subjects in nature. 88. In the 13 RD century, medical teachers and students at Bologna began opening human bodies, leading to the first anatomy textbook based on human dissection by Mondino de Luzzi. 89. New developments in optics played a role in the inception of the Renaissance, both by challenging long-held metaphysical ideas on perception, as well as by contributing to the improvement and development of technology such as the camera obscura and the telescope. At the start of the Renaissance, Roger Bacon, Vitello, and John Peckham each built up a scholastic ontology upon a causal chain beginning with sensation, perception, and finally apperception of the individual and universal forms of Aristotle. 85. Book I. A model of vision later known as perspectivism was exploited and studied by the artists of the Renaissance. This theory uses only 3 of Aristotle's 4 causes: formal, material, and final. 90. In the 16th century, Nicholas Copernicus formulated a heliocentric model of the solar system, stating that the planets revolve around the Sun, instead of the geocentric model where the planets and the Sun revolve around the Earth. This was based on a theorem that the orbital periods of the planets are longer as their orbs are farther from the center of motion, which he found not to agree with Ptolemy's model. 91. Johannes Kepler and others challenged the notion that the only function of the eye is perception, and shifted the main focus in optics from the eye to the propagation of light. 90. 92. Kepler is best known, however, for improving Copernicus' heliocentric model through the discovery of Kepler's laws of planetary motion. Kepler did not reject Aristotelian metaphysics and described his work as a search for the harmony of the spheres. 93. Galileo had made significant contributions to astronomy, physics, and engineering. However, he became persecuted after Pope Urban VIII sentenced him for writing about the heliocentric model. 94. The printing press was widely used to publish scholarly arguments, including some that disagreed widely with contemporary ideas of nature. 95. Francis Bacon and René Descartes published philosophical arguments in favor of a new type of non-Aristotelian science. Bacon emphasized the importance of experiment over contemplation, questioned the Aristotelian concepts of formal and final cause, promoted the idea that science should study the laws of nature and the improvement of all human life. 96. Descartes emphasized individual thought and argued that mathematics rather than geometry should be used to study nature. 97. Age of Enlightenment. Main article, Science in the Age of Enlightenment. See caption. Title page of the 1687 first edition of Philosophiae Naturalis Principia Mathematica by Isaac Newton. At the start of the Age of Enlightenment, Isaac Newton formed the foundation of classical mechanics by his Philosophiae Naturalis Principia Mathematica, greatly influencing future physicists. 98. Gottfried Wilhelm Leibniz incorporated terms from Aristotelian physics, now used in a new non-teleological way. This implied a shift in the view of objects. Objects were now considered as having no innate goals. Leibniz assumed that different types of things all work according to the same general laws of nature, with no special formal or final causes. 99. During this time, the declared purpose and value of science became producing wealth and inventions that would improve human lives, in the materialistic sense of having more food, clothing, and other things. In Bacon's words, the real and legitimate goal of sciences is the endowment of human life with new inventions and riches, and he discouraged scientists from pursuing intangible philosophical or spiritual ideas, which he believed contributed little to human happiness beyond the fume of subtle, sublime or pleasing, speculation. 100. Science during the Enlightenment was dominated by scientific societies, 101, and academies, which had largely replaced universities as centers of scientific research and development. Societies and academies were the backbones of the maturation of the scientific profession. Another important development was the popularization of science among an increasingly literate population. 102. Enlightenment philosophers chose a short history of scientific predecessors, Galileo, Boyle, and Newton principally, as the guides to every physical and social field of the day. 103. The 18th century saw significant advancements in the practice of medicine. 104, and physics. *105, 105, the development of biological taxonomy by Carl Linnaeus. *106, 106, a new understanding of magnetism and electricity. *107, 107, and the maturation of chemistry as a discipline. 108. Ideas on human nature, society, and economics evolved during the Enlightenment. Hume and other Scottish Enlightenment thinkers developed a treatise of human nature, which was expressed historically in works by authors including James Burnet, Adam Ferguson, John Miller, and William Robertson, all of whom merged a scientific study of how humans behaved in ancient and primitive cultures with a strong awareness of the determining forces of modernity. 109. Modern sociology largely originated from this movement. 110. In 1776, Adam Smith published The Wealth of Nations, which is often considered the first work on modern economics. 111. 19th century. Main article, 19th century in science. Sketch of a map with captions. The first diagram of an evolutionary tree made by Charles Darwin in 1837. During the 19th century, many distinguishing characteristics of contemporary modern science began to take shape. These included the transformation of the life and physical sciences, frequent use of precision instruments, emergence of terms such as biologist, physicist, scientist, increased professionalization of those studying nature. Scientists gained cultural authority over many dimensions of society, industrialization of numerous countries, thriving of popular science writings and emergence of science journals. 112. During the late 19th century, psychology emerged as a separate discipline from philosophy when Wilhelm Wundt founded the first laboratory for psychological research in 1879. 113. During the mid-19th century, Charles Darwin and Alfred Russel Wallace independently proposed the theory of evolution by natural selection in 1858, which explained how different plants and animals originated and evolved. Their theory was set out in detail in Darwin's book On the Origin of Species, published in 1859. 114. Separately, Gregor Mendel presented his paper, Experiments on Plant Hybridization in 1865. 115, which outlined the principles of biological inheritance, serving as the basis for modern genetics. 116. Early in the 19th century, John Dalton suggested the modern atomic theory, based on Democritus's original idea of indivisible particles called atoms. 117. The laws of conservation of energy, conservation of momentum and conservation of mass suggested a highly stable universe where there could be little loss of resources. However, with the advent of the steam engine and the Industrial Revolution, there was an increased understanding that not all forms of energy have the same energy qualities, the ease of conversion to useful work or to another form of energy. 118. This realization led to the development of the laws of thermodynamics, in which the free energy of the universe is seen as constantly declining. The entropy of a closed universe increases over time. The electromagnetic theory was established in the 19th century by the works of Hans Christian Ørsted, André-Marie Ampère, Michael Faraday, James Clerk Maxwell, Oliver Heaviside, and Heinrich Hertz. The new theory raised questions that could not easily be answered using Newton's framework. The discovery of X-rays inspired the discovery of radioactivity by Henri Becquerel and Marie Curie in 1896. 121. Marie Curie then became the first person to win 2 Nobel Prizes. 122. In the next year came the discovery of the first subatomic particle, the electron. 123. 20th century. Main article, 20th century in science. Graph showing lower ozone concentration at the South Pole. First global view of the ozone hole in 1983, using a space telescope. In the first half of the century, the development of antibiotics and artificial fertilizers improved human living standards globally. 124. 125. Harmful environmental issues such as ozone depletion, ocean acidification, eutrophication, and climate change came to the public's attention and caused the onset of environmental studies. 126. During this period, scientific experimentation became increasingly larger in scale and funding. 127. The extensive technological innovation stimulated by World War I, World War II, and the Cold War led to competitions between global powers, such as the space race. 128, and nuclear arms race. 129. Substantial international collaborations were also made, despite armed conflicts. 130. In the late 20th century, active recruitment of women and elimination of sex discrimination greatly increased the number of women scientists, but large gender disparities remained in some fields. 131. The discovery of the cosmic microwave background in 1964. 132. Led to a rejection of the steady-state model of the universe in favor of the Big Bang theory of Georges Lemaitre. 133. The century saw fundamental changes within science disciplines. Evolution became a unified theory in the early 20th century when the modern synthesis reconciled Darwinian evolution with classical genetics. 134. Albert Einstein's theory of relativity and the development of quantum mechanics complement classical mechanics to describe physics in extreme length, time and gravity. 135. 136. Widespread use of integrated circuits in the last quarter of the 20th century combined with communications satellites led to a revolution in information technology and the rise of the global internet and mobile computing, including smartphones. The need for mass systematization of long, intertwined causal chains and large amounts of data led to the rise of the fields of systems theory and computer-assisted scientific modeling. 137. 21st century. Main article, 21st Century Science and Technology. Fuzzy donut-shaped blob on a black background. Radio light image of M87* black hole, made by the Earth-spanning Event Horizon Telescope Array in 2019. The Human Genome Project was completed in 2003 by identifying and mapping all of the genes of the human genome, 138. The first induced pluripotent human stem cells were made in 2006, allowing adult cells to be transformed into stem cells and turned to any cell type found in the body, 139. With the affirmation of the Higgs boson discovery in 2013, the last particle predicted by the Standard Model of Particle Physics was found, 140. In 2015, gravitational waves, predicted by general relativity a century before, were first observed, 141, 142. In 2019, the international collaboration event Horizon Telescope presented the first direct image of a black hole's accretion. Branches. Main article, Branches of Science. Modern science is commonly divided into three major branches: natural science, social science, and formal science. 3. Each of these branches comprises various specialized yet overlapping scientific disciplines that often possess their own nomenclature and expertise. 144. Both natural and social sciences are empirical sciences. 145. As their knowledge is based on empirical observations and is capable of being tested for its validity by other researchers working under the same conditions. 146. Natural science. Natural science is the study of the physical world. It can be divided into two main branches, life science and physical science. These two branches may be further divided into more specialized disciplines. For example, physical science can be subdivided into physics, chemistry, astronomy, and earth science. Modern natural science is the successor to the natural philosophy that began in ancient Greece. Galileo, Descartes, Bacon, and Newton debated the benefits of using approaches which were more mathematical and more experimental in a methodical way. Still, philosophical perspectives, conjectures, and presuppositions, often overlooked, remain necessary in natural science. 147. Systematic data collection, including discovery science, succeeded natural history, which emerged in the 16th century by describing and classifying plants, animals, minerals, and so on. 148. Today, natural history suggests observational descriptions aimed at popular audiences. 149. Social science. Two curve crossing over at a point, forming AX shape. Supply and demand curve in economics, crossing over at the optimal equilibrium. Social science is the study of human behavior and functioning of societies. 4. 5. It has many disciplines that include, but are not limited to anthropology, economics, history, human geography, political science, psychology, and sociology. 4. In the social sciences, there are many competing theoretical perspectives, many of which are extended through competing research programs such as the functionalists, conflict theorists, and interactionists in sociology. 4. Due to the limitations of conducting controlled experiments involving large groups of individuals or complex situations, social scientists may adopt other research methods such as the historical method, case studies, and cross-cultural studies. Moreover, if quantitative information is available, social scientists may rely on statistical approaches to better understand social relationships and processes. 4. Formal science. Formal science is an area of study that generates knowledge using formal systems. 156. 7. A formal system is an abstract structure used for inferring theorems from axioms according to a set of rules. 151. It includes mathematics. 152. 153. Systems theory, and theoretical computer science. The formal sciences share similarities with the other two branches by relying on objective, careful, and systematic study of an area of knowledge. They are, however, different from the empirical sciences as they rely exclusively on deductive reasoning, without the need for empirical evidence, to verify their abstract concepts. 11. 154. 146. The formal sciences are therefore a priori disciplines, and because of this, there is disagreement on whether they constitute a science. 8. 155. Nevertheless, the formal sciences play an important role in the empirical sciences. Calculus, for example, was initially invented to understand motion in physics. 156. Natural and social sciences that rely heavily on mathematical applications include mathematical physics. 157. Chemistry. 158. Biology. 159. Finance. 160. And economics. 161. Applied science is the use of the scientific method and knowledge to attain practical goals and includes a broad range of disciplines such as engineering and medicine. 162.14 Engineering is the use of scientific principles to invent, design and build machines, structures and technologies. 163 Science may contribute to the development of new technologies. 164 Medicine is the practice of caring for patients by maintaining and restoring health through the prevention, diagnosis, and treatment of injury or disease. 165 166 The applied sciences are often contrasted with the basic sciences, which are focused on advancing scientific theories and laws that explain and predict events in the natural world. 167 168 Computational science applies computing power to simulate real-world situations, enabling a better understanding of scientific problems than formal mathematics alone can achieve. The use of machine learning and artificial intelligence is becoming a central feature of computational contributions to science, for example in agent-based computational economics, random forests, topic modeling and various forms of prediction. However, machines alone rarely advance knowledge as they require human guidance and capacity to reason, and they can introduce bias against certain social groups or sometimes underperform against humans. 169 170 Interdisciplinary science. Interdisciplinary science involves the combination of two or more disciplines into one. 171 Such as bioinformatics, a combination of biology and computer science. 172 Or cognitive sciences. The concept has existed since the ancient Greek and it became popular again in the 20th century. 173 Scientific research. Scientific research can be labeled as either basic or applied research. Basic research is the search for knowledge and applied research is the search for solutions to practical problems using this knowledge. Most understanding comes from basic research, though sometimes applied research targets specific practical problems. This leads to technological advances that were not previously imaginable. 174 Scientific method. 6 steps of the scientific method in a loop. A diagram variant of scientific method represented as an ongoing process. Scientific research involves using the scientific method, which seeks to objectively explain the events of nature in a reproducible way. 175 Scientists usually take for granted a set of basic assumptions that are needed to justify the scientific method. There is an objective reality shared by all rational observers. This objective reality is governed by natural laws. These laws were discovered by means of systematic observation and experimentation. 2. Mathematics is essential in the formation of hypotheses, theories, and laws, because it is used extensively in quantitative modeling, observing, and collecting measurements. 176. Statistics is used to summarize and analyze data, which allows scientists to assess the reliability of experimental results. 177. In the scientific method, an explanatory thought experiment or hypothesis is put forward as an explanation using parsimony principles and is expected to seek consilience, fitting with other accepted facts related to an observation or scientific question. 178. This tentative explanation is used to make falsifiable predictions, which are typically posted before being tested by experimentation. Disproof of a prediction is evidence of progress. 175. 4-5. 179. Experimentation is especially important in science to help establish causal relationships to avoid the correlation fallacy, though in some sciences such as astronomy or geology, a predicted observation might be more appropriate. 180. When a hypothesis proves unsatisfactory, it is modified or discarded. 181. If the hypothesis survived testing, it may become adopted into the framework of a scientific theory, a validly reasoned, self-consistent model or framework for describing the behavior of certain natural events. A theory typically describes the behavior of much broader sets of observations than a hypothesis. Commonly, a large number of hypotheses can be logically bound together by a single theory. Thus a theory is a hypothesis explaining various other hypotheses. In that vein, theories are formulated according to most of the same scientific principles as hypotheses. Scientists may generate a model, an attempt to describe or depict an observation in terms of a logical, physical or mathematical representation and to generate new hypotheses that can be tested by experimentation. 182. While performing experiments to test hypotheses, scientists may have a preference for one outcome over another. 183, 184, eliminating the bias can be achieved by transparency, careful experimental design, and a thorough peer review process of the experimental results and conclusions. 185, 186. After the results of an experiment are announced or published, it is normal practice for independent researchers to double-check how the research was performed, and to follow up by performing similar experiments to determine how dependable the results might be. 187, taken in its entirety, the scientific method allows for highly creative problem-solving while minimizing the effects of subjective and confirmation bias. 188, intersubjective verifiability, the ability to reach a consensus and reproduce results, is fundamental to the creation of all scientific knowledge. 189. Scientific literature. Main articles, scientific literature and lists of important publications in science. Decorated Nature as title, with scientific text below. Cover of the first issue of Nature, November 4, 1869. Scientific research is published in a range of literature. 190. Scientific journals communicate and document the results of research carried out in universities and various other research institutions, serving as an archival record of science. The first scientific journals, Journal d'Escavans followed by Philosophical Transactions, began publication in 1665. Since that time the total number of active periodicals has steadily increased. In 1981, one estimate for the number of scientific and technical journals in publication was 11,500, 191. Most scientific journals cover a single scientific field and publish the research within that field. The research is normally expressed in the form of a scientific paper. Science has become so pervasive in modern societies that it is considered necessary to communicate the achievements, news, and ambitions of scientists to a wider population. 192. Challenges. The replication crisis is an ongoing methodological crisis that affects parts of the social and life sciences. In subsequent investigations, the results of many scientific studies are proven to be unrepeatable. 193. The crisis has long-standing roots. The phrase was coined in the early 2010s, 194, as part of a growing awareness of the problem. The replication crisis represents an important body of research in metascience, which aims to improve the quality of all scientific research while reducing waste. 195. An area of study or speculation that masquerades as science in an attempt to claim a legitimacy that it would not otherwise be able to achieve is sometimes referred to as pseudoscience, fringe science, or junk science. 196. 197. Physicist Richard Feynman coined the term cargo cult science for cases in which researchers believe and at a glance looks like they are doing science, but lack the honesty allowing their results to be rigorously evaluated. 198. Various types of commercial advertising, ranging from hype to fraud, may fall into these categories. Science has been described as the most important tool for separating valid claims from invalid ones. 199. There can also be an element of political or ideological bias on all sides of scientific debates. Sometimes, research may be characterized as bad science, research that may be well-intended but is incorrect, obsolete, incomplete, or oversimplified expositions of scientific ideas. The term scientific misconduct refers to situations such as where researchers have intentionally misrepresented their published data or have purposely given credit for a discovery to the wrong person. 200. Philosophy of science. Depiction of epicycles, where a planet orbit is going around in a bigger orbit. For Kuhn, the addition of epicycles in Ptolemaic astronomy was normal science within a paradigm, whereas the Copernican revolution was a paradigm shift. There are different schools of thought in the philosophy of science. The most popular position is empiricism, which holds that knowledge is created by a process involving observation. Scientific theories generalize observations. 201. Empiricism generally encompasses inductivism, a position that explains how general theories can be made from the finite amount of empirical evidence available. Many versions of empiricism exist, with the predominant ones being Bayesianism. 202, and the hypothetico-deductive method. 201. Empiricism has stood in contrast to rationalism, the position originally associated with Descartes, which holds that knowledge is created by the human intellect, not by observation. 203. critical rationalism is a contrasting 20th-century approach to science, first defined by Austrian-British philosopher Karl Popper. Popper rejected the way that empiricism describes the connection between theory and observation. He claimed that theories are not generated by observation, but that observation is made in the light of theories, that the only way theory A can be affected by observation is after theory A were to conflict with observation, but theory B were to survive the observation. 204. Popper proposed replacing verifiability with falsifiability as the landmark of scientific theories, replacing induction with falsification as the empirical method. 204. Popper further claimed that there is actually only one universal method, not specific to science, the negative method of criticism, trial and error. 205. Covering all products of the human mind, including science, mathematics, philosophy, and art. 206. Another approach, instrumentalism, emphasizes the utility of theories as instruments for explaining and predicting phenomena. It views scientific theories as black boxes with only their input, initial conditions, and output, predictions, being relevant. Consequences, theoretical entities, and logical structure are claimed to be something that should be ignored. 207. Close to instrumentalism is constructive empiricism, according to which the main criterion for the success of a scientific theory is whether what it says about observable entities is true. 208. Thomas Kuhn argued that the process of observation and evaluation takes place within a paradigm, a logically consistent portrait of the world that is consistent with observations made from its framing. He characterized normal science as the process of observation and puzzle-solving which takes place within a paradigm, whereas revolutionary science occurs when one paradigm overtakes another in a paradigm shift. 209. Each paradigm has its own distinct questions, aims, and interpretations. The choice between paradigms involves setting two or more portraits against the world and deciding which likeness is most promising. A paradigm shift occurs when a significant number of observational anomalies arise in the old paradigm and a new paradigm makes sense of them. That is, the choice of a new paradigm is based on observations, even though those observations are made against the background of the old paradigm. For Kuhn, acceptance or rejection of a paradigm is a social process as much as a logical process. Kuhn's position, however, is not one of relativism. 210. Finally, another approach often cited in debates of scientific skepticism against controversial movements like creation science is methodological naturalism. Naturalists maintain that a difference should be made between natural and supernatural, and science should be restricted to natural explanations. 211. Methodological naturalism maintains that science requires strict adherence to empirical study and independent verification. 212. Scientific community. The scientific community is a network of interacting scientists who conduct scientific research. The community consists of smaller groups working in scientific fields. By having peer review, through discussion and debate within journals and conferences, scientists maintain the quality of research methodology and objectivity when interpreting results. 213. Scientists. Portrait of a middle-aged woman. Marie Curie was the first person to be awarded 2 Nobel Prizes, physics in 1903 and chemistry in 1911, 122. Scientists are individuals who conduct scientific research to advance knowledge in an area of interest. 214, 215. In modern times, many professional scientists are trained in an academic setting and upon completion, attain an academic degree, with the highest degree being a doctorate such as a Doctor of Philosophy or Ph.D. 216. Many scientists pursue careers in various sectors of the economy such as academia, industry, government, and non-profit organizations. 217, 218, 219. Scientists exhibit a strong curiosity about reality and a desire to apply scientific knowledge for the benefit of health, nations, the environment, or industries. Other motivations include recognition by their peers and prestige. In modern times, many scientists have advanced degrees, 220, in an area of science and pursue careers in various sectors of the economy such as academia, industry, government, and non-profit environments. 221, 222. Science has historically been a male-dominated field, with notable exceptions. Women in science faced considerable discrimination in science, much as they did in other areas of male-dominated societies. For example, women were frequently being passed over for job opportunities and denied credit for their work. 223. The achievements of women in science have been attributed to the defiance of their traditional role as laborers within the domestic sphere. 224. Learned societies. Picture of scientists in 200th anniversary of the Prussian Academy of Sciences, 1900. Learned societies for the communication and promotion of scientific thought and experimentation have existed since the Renaissance. 225. Many scientists belong to a learned society that promotes their respective scientific discipline, profession, or group of related disciplines. 226. Membership may either be open to all, require possession of scientific credentials, or conferred by election. 227. Most scientific societies are nonprofit organizations. 228. And many are professional associations. Their activities typically include holding regular conferences for the presentation and discussion of new research results and publishing or sponsoring academic journals in their discipline. Some societies act as professional bodies, regulating the activities of their members in the public interest or the collective interest of the membership. Citation needed. The professionalization of science, begun in the 19th century, was partly enabled by the creation of national distinguished academies of sciences such as the Italian Accademia dei Lincei in 1603, 229, the British Royal Society in 1660, 230, the French Academy of Sciences in 1666, 231, the American National Academy of Sciences in 1863, 232, the German Kaiser Wilhelm Society in 1911, 233, and the Chinese Academy of Sciences in 1949, 234, international scientific organizations, such as the International Science Council, are devoted to international cooperation for science advancement. 235. Awards. Science awards are usually given to individuals or organizations that have made significant contributions to a discipline. They are often given by prestigious institutions, thus it is considered a great honor for a scientist receiving them. Since the early Renaissance, scientists are often awarded medals, money, and titles. The Nobel Prize, a widely regarded prestigious award, is awarded annually to those who have achieved scientific advances in the fields of medicine, physics, and chemistry. 236. Society. Science and society redirects here. Not to be confused with science and society or sociology of scientific knowledge. Funding and policies. See caption. Budget of NASA as percentage of United States federal budget, peaking at 4.4% in 1966 and slowly declining since. Scientific research is often funded through a competitive process in which potential research projects are evaluated and only the most promising receive funding. Such processes, which are run by government, corporations, or foundations, allocate scarce funds. Total research funding in most developed countries is between 1.5% and 3% of GDP. 237. In the OECD, around two-thirds of research and development in scientific and technical fields is carried out by industry, and 20% and 10% respectively by universities and government. The government funding proportion in certain fields is higher, and it dominates research in social science and humanities. In the lesser developed nations, government provides the bulk of the funds for their basic scientific research. 238. Many governments have dedicated agencies to support scientific research, such as the National Science Foundation in the United States. 239. The National Scientific and Technical Research Council in Argentina. 240. Commonwealth Scientific and Industrial Research Organization in Australia. 241. National Center for Scientific Research in France. 242. The Max Planck Society in Germany. 243. And National Research Council in Spain. 244. In commercial research and development, all but the most research-oriented corporations focus more heavily on near-term commercialization possibilities rather than research driven by curiosity. 245. Science policy is concerned with policies that affect the conduct of the scientific enterprise, including research funding, often in pursuance of other national policy goals such as technological innovation to promote commercial product development, weapons development, healthcare, and environmental monitoring. Science policy sometimes refers to the act of applying scientific knowledge and consensus to the development of public policies. In accordance with public policy being concerned about the well-being of its citizens, science policy's goal is to consider how science and technology can best serve the public. 246. Public policy can directly affect the funding of capital equipment and intellectual infrastructure for industrial research by providing tax incentives to those organizations that fund research. 192. NCE and Science Journalism. Dinosaur exhibit in the Houston Museum of Natural Science. Science education for the general public is embedded in the school curriculum and is supplemented by online pedagogical content, for example, YouTube and Khan Academy, museums, and science magazines and blogs. Scientific literacy is chiefly concerned with an understanding of the scientific method, units and methods of measurement, empiricism, a basic understanding of statistics, correlations, qualitative versus quantitative observations, aggregate statistics, as well as a basic understanding of core scientific fields, such as physics, chemistry, biology, ecology, geology and computation. As a student advances into higher stages of formal education, the curriculum becomes more in-depth. Traditional subjects usually included in the curriculum are natural and formal sciences, although recent movements include social and applied science as well. 247. The mass media face pressures that can prevent them from accurately depicting competing scientific claims in terms of their credibility within the scientific community as a whole. Determining how much weight to give different sides in a scientific debate may require considerable expertise regarding the matter. 248. Few journalists have real scientific knowledge, and even beat reporters who are knowledgeable about certain scientific issues may be ignorant about other scientific issues that they are suddenly asked to cover. 249. 250. Science magazines such as New Scientist, Science and Vi, and Scientific American cater to the needs of a much wider readership and provide a non-technical summary of popular areas of research, including notable discoveries and advances in certain fields of research. 251. Science fiction genre, primarily speculative fiction, can transmit the ideas and methods of science to the general public. 252. Recent efforts to intensify or develop links between science and non-scientific disciplines, such as literature or poetry, include the creative writing science resource developed through the Royal Literary Fund. 253. Anti-science attitudes. Main article, Anti-science. While the scientific method is broadly accepted in the scientific community, some fractions of society reject certain scientific positions or are skeptical about science. Examples are the common notion that COVID-19 is not a major health threat to the U.S., held by 39% of Americans in August 2021, 254, or the belief that climate change is not a major threat to the U.S., also held by 40% of Americans, in late 2019 and early 2020. 255. Psychologists have pointed to 4 factors driving rejection of scientific results. Frowny face. 256. Scientific authorities are sometimes seen as inexpert, untrustworthy, or biased. Some marginalized social groups hold anti-science attitudes, in part because these groups have often been exploited in unethical experiments. 257. Messages from scientists may contradict deeply held existing beliefs or morals. The delivery of a scientific message may not be appropriately targeted to a recipient's learning style. Anti-science attitudes seem to be often caused by fear of rejection in social groups. For instance, climate change is perceived as a threat by only 22% of Americans on the right side of the political spectrum, but by 85% on the left. 258. That is, if someone on the left would not consider climate change as a threat, this person may face contempt and be rejected in that social group. In fact, people may rather deny a scientifically accepted fact than lose or jeopardize their social status. 259. Politics. Result in bar graph of 2 questions, is global warming occurring, and are oil/gas companies responsible, showing large discrepancies between American Democrats and Republicans. Public opinion on global warming in the United States by political party. 260. Attitudes towards science are often determined by political opinions and goals. Government, business and advocacy groups have been known to use legal and economic pressure to influence scientific researchers. Many factors can act as facets of the politicization of science, such as anti-intellectualism, perceived threats to religious beliefs, and fear for business interests. 261. politicization of science is usually accomplished when scientific information is presented in a way that emphasizes the uncertainty associated with the scientific evidence. 262. Tactics such as shifting conversation, failing to acknowledge facts, and capitalizing on doubt of scientific consensus have been used to gain more attention for views that have been undermined by scientific evidence. 263. Examples of issues that have involved the politicization of science include the global warming controversy, health effects of pesticides, and health effects of tobacco. 263. 264. Life science. Biologist. Biomedical scientist. 1. Botanist. Clinical pharmaceutical scientist. Herpetologist. Medical laboratory scientist. Microbiologist. Neuroscientist. Physician. Veterinarian. Zoologist. Applied science. Aeronautical engineer. Biomedical engineer. Chemical engineer. Civil engineer. Computer engineer. Educational technologist. 2. Electrical engineer. Engineering technician. Engineering technologist. Mechanical engineer. Petrochemical engineer. Formal science. Computational scientist. Mathematician. 3. A person with an extensive knowledge of mathematics, a field informally defined as being concerned with numbers, data, collection, quantity, structure, space and calculus. Statistics. Actuary. Demographic marketer. Statistician. General scientific occupations. Forensic scientist. 4. Gentleman scientist, a financially independent scientist who pursues scientific study as a hobby. 5. Government scientist. Healthcare science. HIWI, a German abbreviation for assistant scientist. Inventor. Psychologist. Research fellow. School science technician. Science attaché. 6. A member of a diplomatic mission, usually an embassy, that focuses on scientific and technical matters. Scientist. 7. Natural science. Astronaut Bruce McCandless II using manned maneuvering unit outside the United States Space Shuttle Challenger in 1984. Archaeologist. Astronaut. Astronomer. Biochemist. Biologist. Chemist. Ecologist. 8. Forester. Geographer. Naturalist. Oceanographer. Paleontologist. Pathologist. Physical science. Chemist. Physicist. 9. Earth science. Geographer. Geologist. Geoprofessions. Petroleum geologist. Social science. Anthropologist. Economist. Historian. Linguist. Political scientist. Sociologist. Urban planner. The following outline is provided as a topical overview of science. The discipline of science is defined as both the systematic effort of acquiring knowledge through observation, experimentation, and reasoning, and the body of knowledge thus acquired. The word science derives from the Latin word scientia meaning knowledge. A practitioner of science is called a scientist. Modern science respects objective logical reasoning, and follows a set of core procedures or rules to determine the nature and underlying natural laws of all things, with a scope encompassing the entire universe. These procedures, or rules, are known as the scientific method. Essence of science. Research, systematic investigation into existing or new knowledge. Scientific discovery, observation of new phenomena, new actions, or new events and providing new reasoning to explain the knowledge gathered through such observations with previously acquired knowledge from abstract thought and everyday experiences. Laboratory, facility that provides controlled conditions in which scientific research, experiments, and measurement may be performed. Objectivity, the idea that scientists, in attempting to uncover truths about the natural world, must aspire to eliminate personal or cognitive biases, a priori commitments, emotional involvement, etc. Inquiry, any process that has the aim of augmenting knowledge, resolving doubt, or solving a problem. Scientific method. Scientific method, outline, body of techniques for investigating phenomena and acquiring new knowledge, as well as for correcting and integrating previous knowledge. It is based on observable, empirical, measurable evidence, and subject to laws of reasoning, both deductive and inductive. Empirical method. Experimental method. The steps involved to produce a reliable and logical conclusion include conducting initial research and asking a question about a natural phenomenon, making observations of the phenomenon and/or collecting data about it, forming a hypothesis, proposed explanation for a phenomenon, For a hypothesis to be a scientific hypothesis, the scientific method requires that one can test it. Scientists generally base scientific hypotheses on previous observations that cannot satisfactorily be explained with the available scientific theories. Predicting a logical consequence of the hypothesis. Testing the hypothesis through an experiment, methodical procedure carried out with the goal of verifying, falsifying, or establishing the validity of a hypothesis. The three types of scientific experiments are: controlled experiment that compares the results obtained from an experimental sample against a control sample, which is practically identical to the experimental sample except for the one aspect the effect of which is being tested, the independent variable. Natural experiment, empirical study in which the experimental conditions, i.e., which units receive which treatment, are determined by nature or by other factors out of the control of the experimenters, and yet the treatment assignment process is arguably exogenous. Thus, natural experiments are observational studies and are not controlled in the traditional sense of a randomized experiment. Observational study draws inferences about the possible effect of a treatment on subjects, where the assignment of subjects into a treated group versus a control group is outside the control of the investigator. Field experiment applies the scientific method to experimentally examine an intervention in the real world, or as many experimentalists like to say, naturally occurring environments, rather than in the laboratory. See also field research. Gather and analyze data from experiments or observations, including indicators of uncertainty. Draw conclusions by comparing data with predictions. Possible outcomes. Conclusive. The hypothesis is falsified by the data. Data are consistent with the hypothesis. Data are consistent with alternative hypotheses. Inconclusive. Data are not relevant to the hypothesis, or data and predictions are incommensurate. There is too much uncertainty in the data to draw any conclusion. Further steps include peer review and enabling others to reproduce or falsify the observations and/or conclusions. Deductive nomological model. Scientific modeling. Models of scientific method. Hypothetico-deductive model, proposed description of scientific method. According to it, scientific inquiry proceeds by formulating a hypothesis in a form that could conceivably be falsified by a test on observable data. A test that could and does run contrary to predictions of the hypothesis is taken as a falsification of the hypothesis. A test that could but does not run contrary to the hypothesis corroborates the theory. Branches of science. See also, Index of branches of science and list of words ending in ology. Branches of science, divisions within science with respect to the entity or system concerned, which typically embodies its own terminology and nomenclature. The most traditional data structure used for organizing the subfields of science is the tree of knowledge, hence the idea of different scientific branches. But over time, several other taxonomic systems have also been proposed for that purpose, such as networks, tables, or circular schemes. 1. Formal science. Formal science, branches of knowledge that are concerned with formal systems, such as those under the branches of logic, mathematics, computer science, statistics, and some aspects of linguistics. Unlike other sciences, the formal sciences are not concerned with the validity of theories based on observations in the real world, but instead with the properties of formal systems based on definitions and rules. Branches of formal science, also known as the formal sciences. Natural science. Natural science, outline, a major branch of science that tries to explain and predict nature's phenomena based on empirical evidence. In natural science, hypotheses must be verified scientifically to be regarded as scientific theory. Validity, accuracy, and social mechanisms ensuring quality control, such as peer review and repeatability of findings, are among the criteria and methods used for this purpose. Natural science can be broken into two main branches: biology and physical science. Each of these branches, and all of their sub-branches, are referred to as natural sciences. Branches of natural science, also known as the natural sciences. Social science. Main article, outline of social science. Social science, study of the social world constructed between humans. The social sciences usually limit themselves to an anthropomorphically centric view of these interactions with minimal emphasis on the inadvertent impact of social human behavior on the external environment, physical, biological, ecological, etc. Social is the concept of exchange/influence of ideas, thoughts, and relationship interactions, resulting in harmony, peace, self-enrichment, favoritism, maliciousness, justice-seeking, etc., between humans. The scientific method is used in many social sciences, albeit adapted to the needs of the social construct being studied. Branches of social science, also known as the social sciences. Applied science. Applied science, branch of science that applies existing scientific knowledge to develop more practical applications, including inventions and other technological advancements. Branches of applied science, also known as the applied sciences. Philosophy. Philosophy. Types of scientific fields. Exact science, any field of science capable of accurate quantitative expression or precise predictions and rigorous methods of testing hypotheses, especially reproducible experiments involving quantifiable predictions and measurements. Fundamental science, science that describes the most basic objects, forces, relations between them and laws governing them, such that all other phenomena may be in principle derived from them following the logic of scientific reductionism. Hard and soft science, colloquial terms often used when comparing scientific fields of academic research or scholarship, with hard meaning perceived as being more scientific, rigorous, or accurate. Politics of science. Disruptive technology, innovation that helps create a new market and value network, and eventually goes on to disrupt an existing market and value network, over a few years or decades, displacing an earlier technology. Kansas Evolution Hearings, series of hearings held in Topeka, Kansas, United States 5 to May 12, 2005 by the Kansas State Board of Education and its State Board Science Hearing Committee to change how evolution and the origin of life would be taught in the state's public high school science classes. List of books about the politics of science. List of books about the politics of science. Politicization of science. Politicization of science is the manipulation of science for political gain. Science by press release refers to scientists who put an unusual focus on publicizing results of research in the media. History of science. See also, outline of history. History of science. History of science. History of science in general. History of scientific method. History of scientific method is a history of the methodology of scientific inquiry, as differentiated from a history of science in general. Theory/sociology of science, sociology and philosophy of science, as well as the entire field of science studies, have in the 20th century been occupied with the question of large-scale patterns and trends in the development of science, and asking questions about how science works both in a philosophical and practical sense. Historiography, study of the history and methodology of the subdiscipline of history, known as the history of science, including its disciplinary aspects and practices, methods, theories, schools, and to the study of its own historical development. History of science, i.e., the history of the discipline called history of science. History of pseudoscience. History of pseudoscience is the study of pseudoscientific theories over time. A pseudoscience is a set of ideas that presents itself as science, while it does not meet the criteria to properly be called such. Timeline of scientific discoveries shows the date of publication of major scientific theories and discoveries, along with the discoverer. In many cases, the discoveries span several years. Timeline of scientific thought lists the major landmarks across all scientific philosophy and methodological sciences. By period. History of science in early cultures. History of science in early cultures refers to the study of proto-science in ancient history, prior to the development of science in the Middle Ages. History of science in classical antiquity. History of science in classical antiquity encompasses both those inquiries into the workings of the universe aimed at such practical goals as establishing a reliable calendar or determining how to cure a variety of illnesses and those abstract investigations known as natural philosophy. History of science in the Middle Ages. Science in the Middle Ages comprised the study of nature, including practical disciplines, the mathematics and natural philosophy in medieval Europe. History of science in the Renaissance. During the Renaissance, great advances occurred in geography, astronomy, chemistry, physics, mathematics, manufacturing, and engineering. Science and inventions of Leonardo da Vinci, Italian polymath, regarded as the epitome of the Renaissance man, displaying skills in numerous diverse areas of study. Scientific Revolution. Scientific revolution is an era associated primarily with the 16th and 17th centuries during which new ideas and knowledge in physics, astronomy, biology, medicine and chemistry transformed medieval and ancient views of nature and laid the foundations for modern science. Governmental impact on science during World War II. Governmental impact on science during World War II represents the effect of public administration on technological development that provided many advantages to the armed forces, economies and societies in their strategies during the war. By date: 2023 in Science. 20222024. Fields: Archaeology, Space Senescence Research, Technology, Sustainable Energy Research, Computing, Quantum Computing and Communication, Transportation Technology, Biotechnology, Social Sciences, Psychology, Governance and Policy Studies, Paleontology, Paleoanthropology, Dinosaurs, Extinction, Extraterrestrial Environment, Spaceflight, Discovered Exoplanets, Asteroid Close Approaches, Terrestrial Environment, Environment and Environmental Sciences, Climate Change, Tornadoes, Tropical Cyclones, Wildfires, Earthquakes, Weather, Other/related. Science fiction, film, literature, philosophy, timeline of cosmological theories, list of open letters by academics, history of technology by type, list of science timelines. VEET. List of years in science, events related to science or technology which occurred in the listed year, current year in the box on the right. Timeline of scientific discoveries, shows the date of publication of major scientific theories and discoveries, along with the discoverer. In many cases, the discoveries spanned several years. Timeline of scientific experiments, shows the date of publication of major scientific experiments. Timeline of the history of the scientific method, shows an overview of the cultural inventions that have contributed to the development of the scientific method. List of science timelines, more timeline articles. By field. See also, Outline of Technology, History of Technology. History of Natural Science, study of nature and the physical universe that was dominant before the development of modern science. Natural Philosophy, study of nature and the physical universe that was dominant before the development of modern science. Natural History, scientific research of plants or animals, leaning more towards observational rather than experimental methods of study, and encompasses more research published in magazines than in academic journals. History of Biology, traces the study of the living world from ancient to modern times. History of Ecology, history of the science of ecology. History of Molecular Biology, begins in the 1930s with the convergence of various, previously distinct biological disciplines, biochemistry, genetics, microbiology, and virology. History of Astronomy, timeline. History of Chemistry, by 1000 BC, ancient civilizations used technologies that would eventually form the basis of the various branches of chemistry. History of Geography. History of Geology, timeline. History of Meteorology, timeline. History of Physics, as forms of science historically developed out of philosophy. Physics was originally referred to as natural philosophy, a field of study concerned with the workings of nature. History of Science and Technology. History of the Social Sciences, has origin in the common stock of Western philosophy and shares various precursors, but began most intentionally in the early 19th century with the positivist philosophy of science. History of Archaeology, timeline. History of Cognitive Science. History of Criminal Justice. Throughout the history of criminal justice, evolving forms of punishment, added rights for offenders and victims, and policing reforms have reflected changing customs, political ideals, and economic conditions. History of Economics, study of different thinkers and theories in the subject that became political economy and economics from the ancient world to the present day. History of Education, development of systematic methods of teaching and learning. History of Law, study of how law has evolved and why it changed. History of Linguistics, endeavors to describe and explain the human faculty of language. History of Marketing, recognized discipline, along with concomitant changes in marketing theory and practice. History of Parapsychology. History of Political Science, social science discipline concerned with the study of the state, government, and politics. History of Psychology, timeline. History of Sociology, timeline. By region. History of Science in Present States, by continent. C. Category, Science and Technology by continent. History of Science in Historic States. Science and Technology of the Han Dynasty. Science and Technology in the Ottoman Empire. Science and Technology of the Song Dynasty. Science and Technology in the Soviet Union. Science and Technology of the Tang Dynasty. Philosophy of Science. See also, Outline of Philosophy, Philosophy of Science, and Experimental Philosophy. Philosophy of Science, questions the assumptions, foundations, methods and implications of science. Models of scientific inquiry. Adoption, use, results and coordination of science. See also, politics of science, and category, science in society. Science and technology studies. Scientometrics. Altmetrics. Article-level metrics. Expert elicitation. Lists of science and technology awards. Research and development. Innovation. Science policy. Knowledge #science. Funding of science. Technology and mechanisms of science. Timeline of temperature and pressure measurement technology. Laboratory automation. History of communication. Internet research. Scientific journal. Peer review. Metascience. Scientific community. Scientific community, group of all interacting scientists. Scientific organizations. Academy of Sciences, National Academy or another learned society dedicated to sciences. Scientists. Scientist, practitioner of science, an individual who uses scientific method to objectively inquire into the nature of reality, be it the fundamental laws of physics or how people behave. There are many names for scientists, often named in relation to the job that they do. One example of this is a biologist, a scientist who studies biology, the study of living organisms and their environments. Types of scientist. By field. The scientific fields mentioned below are generally described by the science they study. Agricultural scientist, broad multidisciplinary field that encompasses the parts of exact, natural, economic and social sciences that are used in the practice and understanding of agriculture. Archaeologist, study of human activity, primarily through the recovery and analysis of the material culture and environmental data that they have left behind, which includes artifacts, architecture, biofacts and cultural landscapes, the archaeological record. Astronomer. Astronomer is a scientist who studies celestial bodies such as planets, stars and galaxies. Astrophysicist, branch of astronomy that deals with the physics of the universe, including the physical properties of celestial objects, as well as their interactions and behavior. Biologist, scientist devoted to the study of living organisms and their relationship to their environment. Astrobiologist, study of the origin, evolution, distribution, and future of extraterrestrial life. Biophysicist, interdisciplinary science that uses the methods of physical science to study biological systems. Biotechnologist, field of applied biology that involves the use of living organisms and bioprocesses in engineering, technology, medicine and other fields requiring bioproducts. Botanist, discipline of biology, is the science of plant life. Cognitive scientists, scientific study of the mind and its processes. Ecologist, scientific study of the relations that living organisms have with respect to each other and their natural environment. Entomologist, scientific study of insects, a branch of arthropodology. Evolutionary biologist, subfield of biology concerned with the study of the evolutionary processes that have given rise to the diversity of life on Earth. Geneticist, biologist who studies genetics, the science of genes, heredity, and variation of organisms. Herpetologist, branch of zoology concerned with the study of amphibians, including frogs, toads, salamanders, newts, and gymnophiona, and reptiles, including snakes, lizards, amphibians, turtles, terrapins, tortoises, crocodiles, and the tarantulas. Immunologist, branch of biomedical science that covers the study of all aspects of the immune system in all organisms. Ichthyologist, study of fish. Lepidopterist, person who specializes in the study of Lepidoptera, members of an order encompassing moths and the three superfamilies of butterflies, skipper butterflies, and moth butterflies. Marine biologist, scientific study of organisms in the ocean or other marine or brackish bodies of water. Medical scientist, basic research, applied research, or translational research conducted to aid and support the body of knowledge in the field of medicine. Microbiologist, study of microscopic organisms. Mycologist, branch of biology concerned with the study of fungi, including their genetic and biochemical properties, their taxonomy and their use to humans as a source for tinder, medicinals, example, penicillin, food, example, beer, wine, cheese, edible mushrooms, and entheogens, as well as their dangers, such as poisoning or infection. Neuroscientist, individual who studies the scientific field of neuroscience or any of its related subfields. Ornithologist, branch of zoology that concerns the study of birds. Paleontologist, study of prehistoric life. Pathologist, precise study and diagnosis of disease. Pharmacologist, branch of medicine and biology concerned with the study of drug action. Physiologist, science of the function of living systems. Zoologist, branch of biology that relates to the animal kingdom, including the structure, embryology, evolution, classification, habits, and distribution of all animals, both living and extinct. Chemist, scientist trained in the study of chemistry. Analytical chemist, study of the separation, identification, and quantification of the chemical components of natural and artificial materials. Biochemist, study of chemical processes in living organisms, including, but not limited to, living matter. Inorganic chemist, branch of chemistry concerned with the properties and behavior of inorganic compounds. Organic chemist, subdiscipline within chemistry involving the scientific study of the structure, properties, composition, reactions, and preparation, by synthesis or by other means, of carbon-based compounds, hydrocarbons, and their derivatives. Physical chemist, study of macroscopic, atomic, subatomic, and particulate phenomena in chemical systems in terms of physical laws and concepts. Earth scientist, all-embracing term for the sciences related to the planet Earth. Geologist, scientist who studies the solid and liquid matter that constitutes the Earth as well as the processes and history that has shaped it. Glaciologist, study of glaciers, or more generally ice and natural phenomena that involve ice. Hydrologist, study of the movement, distribution, and quality of water on Earth and other planets, including the hydrologic cycle, water resources and environmental watershed sustainability. Limnologist, study of inland waters. Meteorologist, study of weather. Mineralogist, study of chemistry, crystal structure, and physical, including optical, properties of minerals. Oceanographer, branch of earth science that studies the ocean. Paleontologist, study of prehistoric life. Seismologist, scientific study of earthquakes and the propagation of elastic waves through the Earth or through other planet-like bodies. Volcanologist, study of volcanoes, lava, magma, and related geological, geophysical and geochemical phenomena. Informatician, science of information, the practice of information processing, and the engineering of information systems. Computer scientist, scientist who has acquired knowledge of computer science, the study of the theoretical foundations of information and computation. Library scientist, interdisciplinary or multidisciplinary field that applies the practices, perspectives, and tools of management, information technology, education, and other areas to libraries, the collection, organization, preservation, and dissemination of information resources, and the political economy of information. Management scientist, study of advanced analytical methods to help make better decisions. Mathematician, person with an extensive knowledge of mathematics, a field that has been informally defined as being concerned with numbers, data, collection, quantity, structure, space, and change. Statistician, someone who works with theoretical or applied statistics. Military scientist, process of translating national defense policy to produce military capability by employing military scientists, including theorists, researchers, experimental scientists, applied scientists, designers, engineers, test technicians, and military personnel responsible for prototyping. Physicist, scientist who does research in physics. Psychologist, professional or academic title used by individuals who practice psychology. Abnormal psychologist, branch of psychology that studies unusual patterns of behavior, emotion and thought, which may or may not be understood as precipitating a mental disorder. Educational psychologist, psychologist whose differentiating functions may include diagnostic and psychoeducational assessment, psychological counseling in educational communities, students, teachers, parents and academic authorities, community-type psychoeducational intervention, and mediation, coordination, and referral to other professionals, at all levels of the educational system. Biopsychologist, application of the principles of biology, in particular neurobiology, to the study of physiological, genetic, and developmental mechanisms of behavior in human and non-human animals. Clinical psychologist, integration of science, theory and clinical knowledge for the purpose of understanding, preventing, and relieving psychologically based distress or dysfunction and to promote subjective well-being and personal development. Comparative psychologist, scientific study of the behavior and mental processes of non-human animals, especially as these relate to the phylogenetic history, adaptive significance, and development of behavior. Cognitive psychologist, subdiscipline of psychology exploring internal mental processes. It is the study of how people perceive, remember, think, speak, and solve problems. Developmental psychologist, scientific study of systematic psychological changes, emotional changes, and perception changes that occur in human beings over the course of their lifespan. Evolutionary psychologist, approach in the social and natural sciences that examines psychological traits such as memory, perception, and language from a modern evolutionary perspective. Experimental psychologist, study of behavior and the processes that underlie it, by means of experiment. Neuropsychologist, studies the structure and function of the brain as they relate to specific psychological processes and behaviors. Social psychologist, scientific study of how people's thoughts, feelings, and behaviors are influenced by the actual, imagined, or implied presence of others. Social scientist, field of study concerned with society and human behaviors. Anthropologist, study of humanity. Ethnologist, branch of anthropology that compares and analyzes the origins, distribution, technology, religion, language, and social structure of the ethnic, racial, and/or national divisions of humanity. Communication scientist, academic field that deals with processes of human communication, commonly defined as the sharing of symbols to create meaning. Criminologist, study of criminal behavior. Demographer, statistical study of populations. Economist, professional in the social science discipline of economics. Geographer is a scholar whose area of study is geography, the study of Earth's natural environment and human society. Political economist, study of production, buying, and selling, and their relations with law, custom, and government, as well as with the distribution of national income and wealth, including through the budget process. Political scientist, social science discipline concerned with the study of the state, government, and politics. Sociologist. Technologist. Architectural technologist, specialist in the technology of building design and construction. Educational technologist, specialist in tools to enhance learning. Engineering technologist, specialist who implements technology within a field of engineering. Industrial technologist, specialist in the management, operation, and maintenance of complex operation systems. Medical technologist, healthcare professional who performs diagnostic analysis on a variety of body fluids. Radiologic technologist, medical professional who applies doses of radiation for imaging and treatment. Surgical technologist, health specialist who facilitates the conduct of invasive surgical procedures. By employment status. Academic, community of students and scholars engaged in higher education and research. Corporate scientist, someone who is employed by a business to do research and development for the benefit of that business. Layperson, someone who is not an expert or someone who has not had professional training. Gentleman scientist, financially independent scientist who pursues scientific study as a hobby. Government scientist, scientist employed by a country's government. Aristotle, Greek philosopher and polymath, a student of Plato and teacher of Alexander the Great. Archimedes, Greek mathematician, physicist, engineer, inventor, and astronomer. Andreas Vesalius, Flemish anatomist, physician, and author of one of the most influential books on human anatomy, De Humani Corporis Fabrica, on the structure of the human body. Nicholas Copernicus, Renaissance astronomer and the first person to formulate a comprehensive heliocentric cosmology which displaced the Earth from the center of the universe. Galileo Galilei, Italian physicist, mathematician, astronomer, and philosopher who played a major role in the scientific revolution. Johannes Kepler, German mathematician, astronomer and astrologer. A key figure in the 17th century scientific revolution, he is best known for his eponymous laws of planetary motion, codified by later astronomers, based on his works Astronomia Nova, Harmonics Mundi, and Epitome of Copernican Astronomy. René Descartes, French philosopher, mathematician, and writer who spent most of his adult life in the Dutch Republic. Isaac Newton, English physicist, mathematician, astronomer, natural philosopher, alchemist, and theologian, who has been considered by many to be the greatest and most influential scientist who ever lived. Leonhard Euler, pioneering Swiss mathematician and physicist. Pierre-Simon Laplace, French mathematician and astronomer whose work was pivotal to the development of mathematical astronomy and statistics. Alexander von Humboldt, German geographer, naturalist and explorer, and the younger brother of the Prussian minister, philosopher and linguist Wilhelm von Humboldt. Charles Darwin, English naturalist, he established that all species of life have descended over time from common ancestors, and proposed the scientific theory that this branching pattern of evolution resulted from a process that he called natural selection. James Clerk Maxwell, Scottish physicist and mathematician. Marie Curie, Polish physicist and chemist famous for her pioneering research on radioactivity. Albert Einstein, German-born theoretical physicist who developed the theory of general relativity, effecting a revolution in physics. Linus Pauling, American chemist, biochemist, peace activist, author, and educator. He was one of the most influential chemists in history and ranks among the most important scientists of the 20th century. John Bardeen, American physicist and electrical engineer, the only person to have won the Nobel Prize in Physics twice. Frederick Sanger, English biochemist and a two-time Nobel laureate in chemistry, the only person to have been so. Stephen Hawking, British theoretical physicist, cosmologist, and author. Science education. Science education. Scientific literacy encompasses written, numerical, and digital literacy as they pertain to understanding science, its methodology, observations, and theories. Pseudoscholarship is a work, example, publication, lecture, or body of work that is presented as, but is not, the product of rigorous and objective study or research, the act of producing such work, or the pretended learning upon which it is based. Science communication. See also. Icon Science Portal. Outline of academic disciplines. SciMate, open collaboration of scientists using Web 2.0 software to address well-known challenges in academic publishing and technology transfer. Science Daily, news website for topical science articles. Phys.org, news website for topical science articles with some public metrics. Science.tv, virtual community for people interested in science. Sci-Hub, scientific research paper file sharing website. Science Studies. The scientific method is an empirical method for acquiring knowledge that has characterized the development of science since at least the 17th century, with notable practitioners in previous centuries. See the article History of Scientific Method for additional detail. It involves careful observation, applying rigorous skepticism about what is observed, given that cognitive assumptions can distort how one interprets the observation. It involves formulating hypotheses, via induction, based on such observations, the testability of hypotheses, experimental and the measurement-based statistical testing of deductions drawn from the hypotheses, and refinement, or elimination, of the hypotheses based on the experimental findings. These are principles of the scientific method, as distinguished from a definitive series of steps applicable to all scientific enterprises. 1, 2, 3. Although procedures vary from one field of inquiry to another, the underlying process is frequently the same from one field to another. The process in the scientific method involves making conjectures, hypothetical explanations, deriving predictions from the hypotheses as logical consequences, and then carrying out experiments or empirical observations based on those predictions. For a hypothesis is a conjecture, based on knowledge obtained while seeking answers to the question. The hypothesis might be very specific, or it might be broad. Scientists then test hypotheses by conducting experiments or studies. A scientific hypothesis must be falsifiable, implying that it is possible to identify a possible outcome of an experiment or observation that conflicts with predictions deduced from the hypothesis, otherwise, the hypothesis cannot be meaningfully tested. 5. The purpose of an experiment is to determine whether observations A, B, agree with or conflict with the expectations deduced from a hypothesis. 6. Book I, 6.54, pages 372, 408. B. Experiments can take place anywhere from a garage to a remote mountaintop to CERN's Large Hadron Collider. There are difficulties in a formulaic statement of method, however. Though the scientific method is often presented as a fixed sequence of steps, it represents rather a set of general principles. 7. Not all steps take place in every scientific inquiry, nor to the same degree, and they are not always in the same order. 8. 9. History. Main article, History of Scientific Method. See also, Timeline of the History of the Scientific Method. Aristotle, 384 to 322 BCE. As regards his method, Aristotle is recognized as the inventor of scientific method because of his refined analysis of logical implications contained in demonstrative discourse, which goes well beyond natural logic and does not owe anything to the ones who philosophized before him. Ricardo Pozzo, 10. Ibn al-Haytham, 965 to 1039. A polymath, considered by some to be the father of modern scientific methodology, due to his emphasis on experimental data and reproducibility of its results. 11, 12, 13. Johannes Kepler, 1571 to 1630. Kepler shows his keen logical sense in detailing the whole process by which he finally arrived at the true orbit. This is the greatest piece of retroductive reasoning ever performed. C. S. Peirce, circa 1896, on Kepler's reasoning through explanatory hypotheses. 14. Galileo Galilei, 1564 to 1642. According to Albert Einstein, all knowledge of reality starts from experience and ends in it. Propositions arrived at by purely logical means are completely empty as regards reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics, indeed, of modern science altogether. 15. Important debates in the history of science concern skepticism that anything can be known for sure, such as views of Francisco Sanchez, rationalism, especially as advocated by René Descartes, inductivism, empiricism, as argued for by Francis Bacon, then rising to particular prominence with Isaac Newton and his followers, and hypothetico-deductivism, which came to the fore in the early 19th century. The term scientific method emerged in the 19th century, when a significant institutional development of science was taking place and terminologies establishing clear boundaries between science and non-science, such as scientist and pseudoscience, appeared. 16. Throughout the 1830s and 1850s, at which time Baconianism was popular, naturalists like William Whewell, John Herschel, John Stuart Mill engaged in debates over induction and facts and were focused on how to generate knowledge. 16. In the late 19th and early 20th centuries, a debate over realism versus anti-realism was conducted as powerful scientific theories extended beyond the realm of the observable. 17. Problem-solving via scientific method. The term scientific method came into popular use in the 20th century. Dewey's 1910 book, How We Think, inspired popular guidelines. 18. Popping up in dictionaries and science textbooks, although there was little consensus over its meaning. 16. Although there was growth through the middle of the 20th century, by the 1960s and 1970s numerous influential philosophers of science such as Thomas Kuhn and Paul Feyerabend had questioned the universality of the scientific method and in doing so largely replaced the notion of science as a homogeneous and universal method with that of it being a heterogeneous and local practice. 16. In particular, Paul Feyerabend, in the 1975 first edition of his book Against Method, argued against there being any universal rules of science. Wink with a frown. 17. Popper 1963, 19, Gotch 2003, 7, and Toe 2010, 20, disagree with Feyerabend's claim. Problem solvers and researchers are to be prudent with their resources during their inquiry. B. C. Later stances include physicist Lee Smolin's 2013 essay There Is No Scientific Method, 26, in which he espouses two ethical principles, and historian of science Daniel Thursday chapter in the 2015 book Newton's Apple and Other Myths About Science, which concluded that the scientific method is a myth or, at best, an idealization. 27, as myths are beliefs. 28, they are subject to the narrative fallacy as Taleb points out. 29, philosophers Robert Nola and Howard Sankey, in their 2007 book, Theories of Scientific Method, said that debates over scientific method continue, and argued that Feyerabend, despite the title of Against Method, accepted certain rules of method and attempted to justify those rules with a meta-methodology. 30, Staton, 2017, argues it is a mistake to try following rules in the absence of an algorithmic scientific method. In that case, science is best understood through examples. F. But algorithmic methods, such as disproof of existing theory by experiment, have been used since Alhazen, 1027, Book of Optics, B, and Galileo, 1638, Two New Sciences, 32, and the Assayer, 33, still stand as scientific method. They contradict Feyerabend's stance. C. D. The ubiquitous element in the scientific method is empiricism. This is in opposition to stringent forms of rationalism. The scientific method embodies the position that reason alone cannot solve a particular scientific problem. A strong formulation of the scientific method is not always aligned with a form of empiricism in which the empirical data is put forward in the form of experience or other abstracted forms of knowledge. In current scientific practice, however, the use of scientific modeling and reliance on abstract typologies and theories is normally accepted. The scientific method counters claims that revelation, political or religious dogma, appeals to tradition, commonly held beliefs, common sense, or currently held theories pose the only possible means of demonstrating truth. 37, 21, 20. Different early expressions of empiricism and the scientific method can be found throughout history, for instance with the ancient Stoics, Epicurus, 38, Alhazen, E. Avicenna, Al-Biruni, 39, 40, Roger Bacon, and William of Ockham. From the 16th century onwards, experiments were advocated by Francis Bacon, and performed by Giambattista della Porta, 41, Johannes Kepler, 42, I, and Galileo Galilei, J. There was particular development aided by theoretical works by Francisco Sanchez, 43, John Locke, George Berkeley, and David Hume. A sea voyage from America to Europe afforded C.S. Pierce the distance to clarify his ideas, f. gradually resulting in the hypothetico-deductive model, 44, formulated in the 20th century. The model has undergone significant revision since first proposed. For a more formal discussion, see elements of the scientific method. Overview. The DNA example below is a synopsis of this method. The scientific method is the process by which science is carried out. 45, as in other areas of inquiry, science, through the scientific method, can build on previous knowledge and develop a more sophisticated understanding of its topics of study over time. K. 47, 48, 49, 50, 51, 52. This model can be seen to underlie the scientific revolution. 53. Process. The overall process involves making conjectures, hypotheses, deriving predictions from them as logical consequences, and then carrying out experiments based on those predictions to determine whether the original conjecture was correct. 4. There are difficulties in a formulaic statement of method, however. Though the scientific method is often presented as a fixed sequence of steps, these actions are better considered as general principles. 8. Not all steps take place in every scientific inquiry, nor to the same degree, and they are not always done in the same order. As noted by scientist and philosopher William Whewell, 1794 to 1866, invention, sagacity, and genius, 9, are required at every step. Formulation of a question. The question can refer to the explanation of a specific observation, a, as in why is the sky blue, but can also be open-ended, as in how can I design a drug to cure this particular disease? This stage frequently involves finding and evaluating evidence from previous experiments, personal scientific observations or assertions, as well as the work of other scientists. If the answer is already known, a different question that builds on the evidence can be posed. When applying the scientific method to research, determining a good question can be very difficult and it will affect the outcome of the investigation. 54. Hypothesis. A hypothesis is a conjecture, based on knowledge obtained while formulating the question, that may explain any given behavior. The hypothesis might be very specific, for example, Einstein's equivalence principle or Francis Crick's DNA makes RNA makes protein, L, or it might be broad, for example, unknown species of life dwell in the unexplored depths of the oceans. See hypothesis development. A statistical hypothesis is a conjecture about a given statistical population. For example, the population might be people with a particular disease. One conjecture might be that a new drug will cure the disease in some of the people in that population, as in a clinical trial of the drug. 55. A null hypothesis would conjecture that the statistical hypothesis is false, for example, that the new drug does nothing, and that any cure in the population would be caused by chance, a random variable. An alternative to the null hypothesis, to be falsifiable, must say that a treatment program with the drug does better than chance. To test the statement a treatment program with the drug does better than chance, an experiment is designed in which a portion of the population, the control group, is to be left untreated, while another, separate portion of the population is to be treated. 56. T-tests could then specify how large the treated groups, and how large the control groups are to be. In order to infer whether some course of treatment of the population has resulted in a cure of some of them, in each of the groups, m. The groups are examined, in turn by the researchers, in a protocol, n. Strong inference could alternatively propose multiple alternative hypotheses embodied in randomized controlled trials, treatments A, B, C, say in a blinded experiment with varying dosages, or with lifestyle changes, and so forth, so as not to introduce confirmation bias in favor of a specific course of treatment. 58. Ethical considerations could be used to minimize the numbers in the untreated groups. Example, use almost every treatment in every group, but excluding A, B, C, respectively as controls. O, P. Prediction. The prediction step deduces the logical consequences of the hypothesis before the outcome is known. These predictions are expectations for the results of testing. If the result is already known, it is evidence that is ready to be considered in acceptance or rejection of the hypothesis. The evidence is also stronger if the actual result of the predictive test is not already known, as tampering with the test can be ruled out, as can hindsight bias, see post-diction. Ideally, the prediction must also distinguish the hypothesis from likely alternatives. If two hypotheses make the same prediction, observing the prediction to be correct is not evidence for either one over the other. These statements about the relative strength of evidence can be mathematically derived using Bayes' theorem. Q. The consequence, therefore, is to be stated at the same time or briefly after the statement of the hypothesis, but before the experimental result is known. Likewise, the test protocol is to be stated before execution of the test. These requirements become precautions against tampering, and aid the reproducibility of the experiment. Testing. Suitable tests. 23, 22. Of a hypothesis, compare the expected values from the tests of that hypothesis with the actual results of those tests. Scientists, and other people, can then secure, or discard, their hypotheses by conducting suitable experiments. Analysis. An analysis determines, from the results of the experiment, the next actions to take. The expected values from the test of the alternative hypothesis are compared to the expected values resulting from the null hypothesis, that is, a prediction of no difference in the status quo. The difference between expected versus actual indicates which hypothesis better explains the resulting data from the experiment. In cases where an experiment is repeated many times, a statistical analysis such as a chi-squared test whether the null hypothesis is true may be required. Evidence from other scientists, and from experience are available for incorporation at any stage in the process. Depending on the complexity of the experiment, iteration of the process may be required to gather sufficient evidence to answer the question with confidence, or to build up other answers to highly specific questions, to answer a single broader question. When the evidence has falsified the alternative hypothesis, a new hypothesis is required. If the evidence does not conclusively justify discarding the alternative hypothesis, other predictions from the alternative hypothesis might be considered. Pragmatic considerations, such as the resources available to continue inquiry, might guide the investigation's further course. B. When evidence for a hypothesis strongly supports that hypothesis, further questioning can follow, for insight into the broader inquiry under investigation. DNA example. The basic elements of the scientific method are illustrated by the following example, which occurred from 1944 to 1953, from the discovery of the structure of DNA. Question. Previous investigation of DNA had determined its chemical composition, the 4 nucleotides, the structure of each individual nucleotide, and other properties. DNA had been identified as the carrier of genetic information by the Avery-McLeod-McCarty experiment in 1944-59, but the mechanism of how genetic information was stored in DNA was unclear. 60. Hypothesis. Linus Pauling, Francis Crick and James D. Watson hypothesized that DNA had a helical structure. 61. Prediction. If DNA had a helical structure, its X-ray diffraction pattern would be X-shaped. 62. 63. This prediction was determined using the mathematics of the helix transform, which had been derived by Cochrane, Crick, and Vand. 64. And independently by Stokes. This prediction was a mathematical construct, completely independent from the biological problem at hand. Experiment. Rosalind Franklin used pure DNA to perform X-ray diffraction to produce photo 51. The results showed an X-shape. Analysis. When Watson saw the detailed diffraction pattern, he immediately recognized it as a helix. 24, 65, c. He and Crick then produced their model, using this information along with the previously known information about DNA's composition, especially Chargaff's rules of base pairing. 25. The discovery became the starting point for many further studies involving the genetic material, such as the field of molecular genetics, and it was awarded the Nobel Prize in 1962. Each step of the example is examined in more detail later in the article. Other components. The scientific method also includes other components required even when all the iterations of the steps above have been completed. Frowny face 32. Replication. If an experiment cannot be repeated to produce the same results, this implies that the original results might have been in error. As a result, it is common for a single experiment to be performed multiple times, especially when there are uncontrolled variables or other indications of experimental error. For significant or surprising results, other scientists may also attempt to replicate the results for themselves, especially if those results would be important to their own work. 66. Replication has become a contentious issue in social and biomedical science where treatments are administered to groups of individuals. Typically, an experimental group gets the treatment, such as a drug, and the control group gets a placebo. John Ioannidis in 2005 pointed out that the method being used has led to many findings that cannot be replicated. 67. External review. The process of peer review involves evaluation of the experiment by experts, who typically give their opinions anonymously. Some journals request that the experimenter provide lists of possible peer reviewers, especially if the field is highly specialized. Peer review does not certify the correctness of the results, only that, in the opinion of the reviewer, the experiments themselves were sound, based on the description supplied by the experimenter. If the work passes peer review, which occasionally may require new experiments requested by the reviewers, it will be published in a peer-reviewed scientific journal. The specific journal that publishes the results indicates the perceived quality of the work. R. Data recording and sharing. Scientists typically are careful in recording their data, a requirement promoted by Ludwig Fleck, 1896–1961, and others. 68. Though not typically required, they might be requested to supply this data to other scientists who wish to replicate their original results, or parts of their original results, extending to the sharing of any experimental samples that may be difficult to obtain. 69. See communication and community. Instrumentation. See scientific community, big science. Institutional researchers might acquire an instrument to institutionalize their tests. These instruments would use observations of the real world, which might agree with, or perhaps conflict with, their predictions deduced from their hypothesis. These institutions thereby reduce the research function to a cost/benefit, 70, which is expressed as money, and the time and attention of the researchers to be expended, 70, in exchange for a report to their constituents, 71. Current large instruments, such as CERN's Large Hadron Collider, LHC, 72, or LIGO, 73, or the National Ignition Facility, NIF, 74, or the International Space Station, ISS, 75, or the James Webb Space Telescope, JWST, 76, 77, entail expected costs of billions of dollars, and timeframes extending over decades. These kinds of institutions affect public policy, on a national or even international basis, and the researchers would require shared access to such machines and their adjunct infrastructure. 78. See perceptual control theory, open-loop and closed-loop feedback. Elements of the scientific method. There are different ways of outlining the basic method used for scientific inquiry. The scientific community and philosophers of science generally agree on the following classification of method components. These methodological elements and organization of procedures tend to be more characteristic of experimental sciences than social sciences. Nonetheless, the cycle of formulating hypotheses, testing and analyzing the results, and formulating new hypotheses, will resemble the cycle described below. The scientific method is an iterative, cyclical process through which information is continually revised. 79, 80. It is generally recognized to develop advances in knowledge through the following elements, in varying combinations or contributions. Frowny face 48, 51. Characterizations, observations, definitions, and measurements of the subject of inquiry. Hypotheses, theoretical, hypothetical explanations of observations and measurements of the subject. Predictions, inductive and deductive reasoning from the hypothesis or theory. Experiments, tests of all of the above. Each element of the scientific method is subject to peer review for possible mistakes. These activities do not describe all that scientists do but apply mostly to experimental sciences, example, physics, chemistry, biology, and psychology. The elements above are often taught in the educational system as the scientific method. The scientific method is not a single recipe, it requires intelligence, imagination, and creativity. 81. In this sense, it is not a mindless set of standards and procedures to follow, but is rather an ongoing cycle, constantly developing more useful, accurate, and comprehensive models and methods. For example, when Einstein developed the special and general theories of relativity, he did not in any way refute or discount Newton's Principia. On the contrary, if the astronomically massive, the feather light, and the extremely fast are removed from Einstein's theories, all phenomena Newton could not have observed, Newton's equations are what remain. Einstein's theories are expansions and refinements of Newton's theories and, thus, increase confidence in Newton's work. An iterative, 80, pragmatic, 37, scheme of the 4 points above is sometimes offered as a guideline for proceeding. Frowny face 82. Define a question. Gather information and resources, observe. Form an explanatory hypothesis. Test the hypothesis by performing an experiment and collecting data in a reproducible manner. Analyze the data. Interpret the data and draw conclusions that serve as a starting point for a new hypothesis. Publish results. Retest, frequently done by other scientists. The iterative cycle inherent in this step-by-step method goes from point 3 to 6 back to 3 again. While this schema outlines a typical hypothesis/testing method, 83, many philosophers, historians, and sociologists of science, including Paul Feyerabend, T., claim that such descriptions of scientific method have little relation to the ways that science is actually practiced. Characterizations. The scientific method depends upon increasingly sophisticated characterizations of the subjects of investigation. The subjects can also be called unsolved problems or the unknowns. For example, Benjamin Franklin conjectured, correctly, that St. Elmo's fire was electrical in nature, but it has taken a long series of experiments and theoretical changes to establish this. While seeking the pertinent properties of the subjects, careful thought may also entail some definitions and observations. The observations often demand careful measurements and/or counting. The systematic, careful collection of measurements or counts of relevant quantities is often the critical difference between pseudosciences, such as alchemy, and science, such as chemistry or biology. Scientific measurements are usually tabulated, graphed, or mapped, and statistical manipulations, such as correlation and regression, performed on them. The measurements might be made in a controlled setting, such as a laboratory, or made on more or less inaccessible or unmanipulatable objects such as stars or human populations. The measurements often require specialized scientific instruments such as thermometers, spectroscopes, particle accelerators, or voltmeters, and the progress of a scientific field is usually intimately tied to their invention and improvement. I am not accustomed to saying anything with certainty after only 1 or 2 observations. The scientific method is not a single recipe. It requires intelligence, imagination, and creativity. 81. In this sense, it is not a mindless set of standards and procedures to follow, but is rather an ongoing cycle, constantly developing more useful, accurate, and comprehensive models and methods. For example, when Einstein developed the special and general theories of relativity, he did not in any way refute or discount Newton's Principia. On the contrary, if the astronomically massive, the feather light, and the extremely fast are removed from Einstein's theories, all phenomena Newton could not have observed, Newton's equations are what remain. Einstein's theories are expansions and refinements of Newton's theories and, thus, increase confidence in Newton's work. An iterative, 80, pragmatic, 37, scheme of the 4 points above is sometimes offered as a guideline for proceeding. Frowny face 82. Define a question. Gather information and resources, observe. Form an explanatory hypothesis. Test the hypothesis by performing an experiment and collecting data in a reproducible manner. Analyze the data. Interpret the data and draw conclusions that serve as a starting point for a new hypothesis. Publish results. Retest, frequently done by other scientists. The iterative cycle inherent in this step-by-step method goes from point 3 to 6 back to 3 again. While this schema outlines a typical hypothesis/testing method, 83, many philosophers, historians, and sociologists of science, including Paul Feyerabend, claim that such descriptions of scientific method have little relation to the ways that science is actually practiced. Characterizations. The scientific method depends upon increasingly sophisticated characterizations of the subjects of investigation. The subjects can also be called unsolved problems or the unknowns. For example, Benjamin Franklin conjectured, correctly, that St. Elmo's fire was electrical in nature, but it has taken a long series of experiments and theoretical changes to establish this. While seeking the pertinent properties of the subjects, careful thought may also entail some definitions and observations. The observations often demand careful measurements and/or counting. The systematic, careful collection of measurements or counts of relevant quantities is often the critical difference between pseudosciences, such as alchemy, and science, such as chemistry or biology. Scientific measurements are usually tabulated, graphed, or mapped, and statistical manipulations, such as correlation and regression, performed on them. The measurements might be made in a controlled setting, such as a laboratory, or made on more or less inaccessible or unmanipulatable objects such as stars or human populations. The measurements often require specialized scientific instruments such as thermometers, spectroscopes, particle accelerators, or voltmeters, and the progress of a scientific field is usually intimately tied to their invention and improvement. I am not accustomed to saying anything with certainty after only one or two observations. Uncertainty. Measurements in scientific work are also usually accompanied by estimates of their uncertainty. 70. The uncertainty is often estimated by making repeated measurements of the desired quantity. Uncertainties may also be calculated by consideration of the uncertainties of the individual underlying quantities used. Counts of things, such as the number of people in a nation at a particular time, may also have an uncertainty due to data collection limitations. Or counts may represent a sample of desired quantities, with an uncertainty that depends upon the sampling method used and the number of samples taken. Definition. Measurements demand the use of operational definitions of relevant quantities. That is, a scientific quantity is described or defined by how it is measured, as opposed to some more vague, inexact, or idealized definition. For example, electric current, measured in amperes, may be operationally defined in terms of the mass of silver deposited in a certain time on an electrode in an electrochemical device that is described in some detail. The operational definition of a thing often relies on comparisons with standards. The operational definition of mass ultimately relies on the use of an artifact, such as a particular kilogram of platinum iridium kept in a laboratory in France. The scientific definition of a term sometimes differs substantially from its natural language usage. For example, mass and weight overlap in meaning in common discourse, but have distinct meanings in mechanics. Scientific quantities are often characterized by their units of measure, which can later be described in terms of conventional physical units when communicating the work. New theories are sometimes developed after realizing certain terms have not previously been sufficiently clearly defined. For example, Albert Einstein's first paper on relativity begins by defining simultaneity and the means for determining length. These ideas were skipped over by Isaac Newton with, "I do not define time, space, place and motion," as being well known to all. Einstein's paper then demonstrates that they, viz., absolute time and length independent of motion, were approximations. Francis Crick cautions us that when characterizing a subject, however, it can be premature to define something when it remains ill understood. 86. In Crick's study of consciousness, he actually found it easier to study awareness in the visual system, rather than to study free will, for example. His cautionary example was the gene. The gene was much more poorly understood before Watson and Crick's pioneering discovery of the structure of DNA. It would have been counterproductive to spend much time on the definition of the gene, before them. DNA characterizations. The history of the discovery of the structure of DNA is a classic example of the elements of the scientific method. In 1950 it was known that genetic inheritance had a mathematical description, starting with the studies of Gregor Mendel, and that DNA contained genetic information, Oswald Avery's transforming principle. 59. But the mechanism of storing genetic information, i.e., genes, in DNA was unclear. Researchers in Bragg's laboratory at Cambridge University made X-ray diffraction pictures of various molecules, starting with crystals of salt, and proceeding to more complicated substances. Using clues painstakingly assembled over decades, beginning with its chemical composition, it was determined that it should be possible to characterize the physical structure of DNA, and the X-ray images would be the vehicle. 87. 2. DNA hypotheses. Another example, precession of Mercury. Precession of the perihelion, exaggerated in the case of Mercury, but observed in the case of S2's apsidal precession around Sagittarius A*. 88. The characterization element can require extended and extensive study, even centuries. It took thousands of years of measurements, from the Chaldean, Indian, Persian, Greek, Arabic, and European astronomers, to fully record the motion of planet Earth. Newton was able to include those measurements into the consequences of his laws of motion. But the perihelion of the planet Mercury's orbit exhibits a precession that cannot be fully explained by Newton's laws of motion, see diagram to the right, as Leverrier pointed out in 1859. The observed difference for Mercury's precession between Newtonian theory and observation was one of the things that occurred to Albert Einstein as a possible early test of his theory of general relativity. His relativistic calculations matched observation much more closely than did Newtonian theory. The difference is approximately 43 arcseconds per century. Hypothesis development. Main article, hypothesis formation. A hypothesis is a suggested explanation of a phenomenon, or alternately a reasoned proposal suggesting a possible correlation between or among a set of phenomena. Normally hypotheses have the form of a mathematical model. Sometimes, but not always, they can also be formulated as existential statements, stating that some particular instance of the phenomenon being studied has some characteristic and causal explanations, which have the general form of universal statements, stating that every instance of the phenomenon has a particular characteristic. Scientists are free to use whatever resources they have, their own creativity, ideas from other fields, inductive reasoning, Bayesian inference, and so on, to imagine possible explanations for a phenomenon under study. Albert Einstein once observed that there is no logical bridge between phenomena and their theoretical principles. 89. Charles Sanders Peirce, borrowing a page from Aristotle, Prior Analytics, 2.25, 91, described the incipient stages of inquiry, instigated by the irritation of doubt to venture a plausible guess, as abductive reasoning. 34. 2. Page 290. The history of science is filled with stories of scientists claiming a flash of inspiration, or a hunch, which then motivated them to look for evidence to support or refute their idea. Michael Polanyi made such creativity the centerpiece of his discussion of methodology. William Glenn observes that, 92. The success of a hypothesis, or its service to science, lies not simply in its perceived truth, or power to displace, subsume or reduce a predecessor idea, but perhaps more in its ability to stimulate the research that will illuminate bald suppositions and areas of vagueness. William Glenn, The Mass Extinction Debates. In general, scientists tend to look for theories that are elegant or beautiful. Scientists often use these terms to refer to a theory that is following the known facts but is nevertheless relatively simple and easy to handle. Occam's razor serves as a rule of thumb for choosing the most desirable amongst a group of equally explanatory hypotheses. To minimize the confirmation bias which results from entertaining a single hypothesis, strong inference emphasizes the need for entertaining multiple alternative hypotheses. 58. DNA hypotheses. Linus Pauling proposed that DNA might be a triple helix. 93. This hypothesis was also considered by Francis Crick and James D. Watson but discarded. When Watson and Crick learned of Pauling's hypothesis, they understood from existing data that Pauling was wrong. 94. And that Pauling would soon admit his difficulties with that structure. So, the race was on to figure out the correct structure, except that Pauling did not realize at the time that he was in a race. 3. DNA predictions. Predictions from the hypothesis. Main article, Prediction in Science. Any useful hypothesis will enable predictions, by reasoning including deductive reasoning. It might predict the outcome of an experiment in a laboratory setting or the observation of a phenomenon in nature. The prediction can also be statistical and deal only with probabilities. It is essential that the outcome of testing such a prediction be currently unknown. Only in this case does a successful outcome increase the probability that the hypothesis is true. If the outcome is already known, it is called a consequence and should have already been considered while formulating the hypothesis. If the predictions are not accessible by observation or experience, the hypothesis is not yet testable and so will remain to that extent unscientific in a strict sense. A new technology or theory might make the necessary experiments feasible. For example, while a hypothesis on the existence of other intelligent species may be convincing with scientifically based speculation, no known experiment can test this hypothesis. Therefore, science itself can have little to say about the possibility. In the future, a new technique may allow for an experimental test and the speculation would then become part of accepted science. DNA predictions. James D. Watson, Francis Crick, and others hypothesized that DNA had a helical structure. This implied that DNA's X-ray diffraction pattern would be X-shaped. 63, 62. This prediction followed from the work of Cochrane, Crick and Van, 64, and independently by Stokes. The Cochrane-Crick-Van Stokes theorem provided a mathematical explanation for the empirical observation that diffraction from helical structures produces X-shaped patterns. In their first paper, Watson and Crick also noted that the double helix structure they proposed provided a simple mechanism for DNA replication, writing, "It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material." 95, 4. DNA experiments. Another example, general relativity. Einstein's prediction, 1907 light bends in a gravitational field. Einstein's theory of general relativity makes several specific predictions about the observable structure of spacetime, such as that light bends in a gravitational field, and that the amount of bending depends in a precise way on the strength of that gravitational field. Arthur Eddington's observations made during a 1919 solar eclipse supported general relativity rather than Newtonian gravitation. 96. Experiments. Main article, Experiment. Once predictions are made, they can be sought by experiments. If the test results contradict the predictions, the hypotheses which entailed them are called into question and become less tenable. Sometimes the experiments are conducted incorrectly or are not very well designed when compared to a crucial experiment. If the experimental results confirm the predictions, then the hypotheses are considered more likely to be correct, but might still be wrong and continue to be subject to further testing. The experimental control is a technique for dealing with observational error. This technique uses the contrast between multiple samples, or observations, or populations, under differing conditions, to see what varies or what remains the same. We vary the conditions for the acts of measurement, to help isolate what has changed. Mills' canons can then help us figure out what the important factor is. 97. Factor analysis is one technique for discovering the important factor in an effect. Depending on the predictions, the experiments can have different shapes. It could be a classical experiment in a laboratory setting, a double-blind study, or an archaeological excavation. Even taking a plane from New York to Paris is an experiment that tests the aerodynamical hypotheses used for constructing the plane. Scientists assume an attitude of openness and accountability on the part of those experimenting. Detailed record keeping is essential to aid in recording and reporting on the experimental results, and supports the effectiveness and integrity of the procedure. They will also assist in reproducing the experimental results, likely by others. Traces of this approach can be seen in the work of Hipparchus, 190 to 120 BCE, when determining a value for the precession of the Earth, while controlled experiments can be seen in the works of al-Battani, 853 to 929 CE, 98, and Alhazen, 965 to 1039 CE. 6. V. W. G. DNA experiments. Watson and Crick showed an initial, and incorrect, proposal for the structure of DNA to a team from King's College London, Rosalind Franklin, Maurice Wilkins, and Raymond Gosling. Franklin immediately spotted the flaws which concerned the water content. Later Watson saw Franklin's detailed X-ray diffraction images which showed an X shape, 100, and was able to confirm the structure was helical, 24, 65. This rekindled Watson and Crick's model building and led to the correct structure. 1. DNA characterizations. Evaluation and improvement. The scientific method is iterative. At any stage, it is possible to refine its accuracy and precision, so that some consideration will lead the scientist to repeat an earlier part of the process. Failure to develop an interesting hypothesis may lead a scientist to redefine the subject under consideration. Failure of a hypothesis to produce interesting and testable predictions may lead to reconsideration of the hypothesis or of the definition of the subject. Failure of an experiment to produce interesting results may lead a scientist to reconsider the experimental method, the hypothesis, or the definition of the subject. By 1027, Alhazen, based on his measurements of the refraction of light, was able to deduce that outer space was less dense than air, that is, the body of the heavens is rarer than the body of air. 36. In 1079 Ibn Muaydih's treatise on twilight was able to infer that Earth's atmosphere was 50 miles thick, based on atmospheric refraction of the sun's rays, x. Other scientists may start their own research and enter the process at any stage. They might adopt the characterization and formulate their own hypothesis, or they might adopt the hypothesis and deduce their own predictions. Often the experiment is not done by the person who made the prediction, and the characterization is based on experiments done by someone else. Published results of experiments can also serve as a hypothesis predicting their own reproducibility. DNA iterations. After considerable fruitless experimentation, being discouraged by their superior from continuing, and numerous false starts, 102, 103, 104, Watson and Crick were able to infer the essential structure of DNA by concrete modeling of the physical shapes of the nucleotides which comprise it, 25, 105, 106. They were guided by the bond lengths which had been deduced by Linus Pauling and by Rosalind Franklin's X-ray diffraction images. DNA example. Confirmation. Science is a social enterprise, and scientific work tends to be accepted by the scientific community when it has been confirmed. Crucially, experimental and theoretical results must be reproduced by others within the scientific community. Researchers have given their lives for this vision. George Wilhelm Richman was killed by ball lightning, 1753, when attempting to replicate the 1752 kite-flying experiment of Benjamin Franklin, 107. To protect against bad science and fraudulent data, government research-granting agencies such as the National Science Foundation and science journals, including Nature and Science, have a policy that researchers must archive their data and methods so that other researchers can test the data and methods and build on the research that has gone before. Scientific data archiving can be done at several national archives in the U.S. or the World Data Center. Scientific inquiry. Scientific inquiry generally aims to obtain knowledge in the form of testable explanations, 23, 22, that scientists can use to predict the results of future experiments. This allows scientists to gain a better understanding of the topic under study, and later to use that understanding to intervene in its causal mechanisms, such as to cure disease. The better an explanation is at making predictions, the more useful it frequently can be, and the more likely it will continue to explain a body of evidence better than its alternatives. The most successful explanations, those which explain and make accurate predictions in a wide range of circumstances, are often called scientific theories. Most experimental results do not produce large changes in human understanding. Improvements in theoretical scientific understanding typically result from a gradual process of development over time, sometimes across different domains of science. 108. Scientific models vary in the extent to which they have been experimentally tested and for how long, and in their acceptance in the scientific community. In general, explanations become accepted over time as evidence accumulates on a given topic, and the explanation in question proves more powerful than its alternatives at explaining the evidence. Often subsequent researchers reformulate the explanations over time, or combined explanations to produce new explanations. Toe sees the scientific method in terms of an evolutionary algorithm applied to science and technology. 20. See ceteris paribus, and mutatis mutandis. Properties of scientific inquiry. Scientific knowledge is closely tied to empirical findings and can remain subject to falsification if new experimental observations are incompatible with what is found. That is, no theory can ever be considered final since new problematic evidence might be discovered. If such evidence is found, a new theory may be proposed, or, more commonly, it is found that modifications to the previous theory are sufficient to explain the new evidence. The strength of a theory relates to how long it has persisted without major alteration to its core principles. See invariant explanations. Theories can also become subsumed by other theories. For example, Newton's laws explained thousands of years of scientific observations of the planets almost perfectly. However, these laws were then determined to be special cases of a more general theory, relativity, which explained both the previously unexplained exceptions to Newton's laws and predicted and explained other observations such as the deflection of light by gravity. Thus, in certain cases independent, unconnected, scientific observations can be connected, unified by principles of increasing explanatory power. 109, 110. Since new theories might be more comprehensive than what preceded them, and thus be able to explain more than previous ones, successor theories might be able to meet a higher standard by explaining a larger body of observations than their predecessors. 109. For example, the theory of evolution explains the diversity of life on Earth, how species adapt to their environments, and many other patterns observed in the natural world. Wink with a frown. 111. 112. Its most recent major modification was unification with genetics to form the modern evolutionary synthesis. In subsequent modifications, it has also subsumed aspects of many other fields such as biochemistry and molecular biology. 20. Beliefs and biases. Flying Gallop, as shown by this painting, Theodore Géricault, 1821, is falsified, see below. Muybridge's photographs of the horse in motion, 1878, were used to answer the question of whether all 4 feet of a galloping horse are ever off the ground at the same time. This demonstrates a use of photography as an experimental tool in science. Scientific methodology often directs that hypotheses be tested in controlled conditions wherever possible. This is frequently possible in certain areas, such as in the biological sciences, and more difficult in other areas, such as in astronomy. The practice of experimental control and reproducibility can have the effect of diminishing the potentially harmful effects of circumstance, and to a degree, personal bias. For example, pre-existing beliefs can alter the interpretation of results, as in confirmation bias. This is a heuristic that leads a person with a particular belief to see things as reinforcing their belief, even if another observer might disagree. In other words, people tend to observe what they expect to observe. 28. He action of thought is excited by the irritation of doubt, and ceases when belief is attained. C.S. Peirce, How to Make Our Ideas Clear, 1877, 34. A historical example is the belief that the legs of a galloping horse are splayed at the point when none of the horse's legs touch the ground, to the point of this image being included in paintings by its supporters. However, the first stop-action pictures of a horse's gallop by Edward Muybridge showed this to be false, and that the legs are instead gathered together. 113. Another important human bias that plays a role is a preference for new, surprising statements, see appeal to novelty, which can result in a search for evidence that the new is true. 114. Poorly attested beliefs can be believed and acted upon via a less rigorous heuristic. 115. Goldhaber and Nieto published in 2010 the observation that if theoretical structures with many closely neighboring subjects are described by connecting theoretical concepts, then the theoretical structure acquires a robustness which makes it increasingly hard, though certainly never impossible, to overturn. 110. When a narrative is constructed, its elements become easier to believe. 116, 29. Fleck 1979, page 27 notes words and ideas are originally phonetic and mental equivalences of the experiences coinciding with them. Such proto-ideas are at first always too broad and insufficiently specialized. Once a structurally complete and closed system of opinions consisting of many details and relations has been formed, it offers enduring resistance to anything that contradicts it. Sometimes, these relations have their elements assumed a priori, or contain some other logical or methodological flaw in the process that ultimately produced them. Donald M. McKay has analyzed these elements in terms of limits to the accuracy of measurement and has related them to instrumental elements in a category of measurement. Why? Models of scientific inquiry. Classical model. The classical model of scientific inquiry derives from Aristotle, 117, who distinguished the forms of approximate and exact reasoning, set out the threefold scheme of abductive, deductive, and inductive inference, and also treated the compound forms such as reasoning by analogy. Hypothetico-deductive model. The hypothetico-deductive model or method is a proposed description of the scientific method. Here, predictions from the hypothesis are central. If you assume the hypothesis to be true, what consequences follow? If a subsequent empirical investigation does not demonstrate that these consequences or predictions correspond to the observable world, the hypothesis can be concluded to be false. Pragmatic model. See also, pragmatic theory of truth. In 1877, 48, Charles Sanders Peirce, 1839–1914, characterized inquiry in general not as the pursuit of truth per se but as the struggle to move from irritating, inhibitory doubts born of surprises, disagreements, and the like, and to reach a secure belief, the belief being that on which one is prepared to act. He framed scientific inquiry as part of a broader spectrum and is spurred, like inquiry generally, by actual doubt, not mere verbal or hyperbolic doubt, which he held to be fruitless. He outlined 4 methods of settling opinion, ordered from least to most successful. The method of tenacity, policy of sticking to initial belief, which brings comforts and decisiveness but leads to trying to ignore contrary information and others' views as if truth were intrinsically private, not public. It goes against the social impulse and easily falters since one may well notice when another's opinion is as good as one's own initial opinion. Its successes can shine but tend to be transitory. The method of authority, which overcomes disagreements but sometimes brutally. Its successes can be majestic and long-lived, but it cannot operate thoroughly enough to suppress doubts indefinitely, especially when people learn of other societies present and past. The method of the a priori, which promotes conformity less brutally but fosters opinions as something like tastes, arising in conversation and comparisons of perspectives in terms of what is agreeable to reason. Thereby it depends on fashion in paradigms and goes in circles over time. It is more intellectual and respectable but, like the first 2 methods, sustains accidental and capricious beliefs, destining some minds to doubt it. The scientific method, the method wherein inquiry regards itself as fallible and purposely tests itself and criticizes, corrects, and improves itself. Peirce held that slow, stumbling ratiocination can be dangerously inferior to instinct and traditional sentiment in practical matters, and that the scientific method is best suited to theoretical research, 120, which in turn should not be trammeled by the other methods in practical ends. Reason's first rule is that, in order to learn, one must desire to learn and, as a corollary, must not block the way of inquiry. 21. The scientific method excels the others by being deliberately designed to arrive, eventually, at the most secure beliefs, upon which the most successful practices can be based. Starting from the idea that people seek not truth per se but instead to subdue irritating, inhibitory doubt, Peirce showed how, through the struggle, some can come to submit to the truth for the sake of belief's integrity, seek as truth the guidance of potential practice correctly to its given goal, and wed themselves to the scientific method. 48-51. For Peirce, rational inquiry implies presuppositions about truth and the real. To reason is to presuppose, and at least to hope, as a principle of the reasoner's self-regulation, that the real is discoverable and independent of our vagaries of opinion. In that vein, he defined truth as the correspondence of a sign, in particular, a proposition, to its object and, pragmatically, not as the actual consensus of some definite, finite community, such that to inquire would be to poll the experts, but instead as that final opinion which all investigators would reach sooner or later but still inevitably, if they were to push investigation far enough, even when they start from different points. 34. In tandem he defined the real as a true science. Object, be that object a possibility or quality, or an actuality or brute fact, or a necessity or norm or law, which is what it is independently of any finite community's opinion and, pragmatically, depends only on the final opinion destined in a sufficient investigation. That is a destination as far, or near, as the truth itself to you or me or the given finite community. Thus, his theory of inquiry boils down to do the science. Those conceptions of truth and the real involve the idea of a community both without definite limits, and thus potentially self-correcting as far as needed, and capable of definite increase of knowledge. 121. As inference, logic is rooted in the social principle since it depends on a standpoint that is, in a sense, unlimited. 122. Paying special attention to the generation of explanations, Peirce outlined the scientific method as coordination of 3 kinds of inference in a purposeful cycle aimed at settling doubts, as follows, in 3-4 in a neglected argument, 4, except as otherwise noted. Abduction or retroduction. Guessing, inference to explanatory hypotheses for selection of those best worth trying. From abduction, Peirce distinguishes induction as inferring, based on tests, the proportion of truth in the hypothesis. Every inquiry, whether into ideas, brute facts, or norms and laws, arises from surprising observations in one or more of those realms, and for example at any stage of an inquiry already underway. All explanatory content of theories comes from abduction, which guesses a new or outside idea to account in a simple, economical way for a surprising or complicated phenomenon. Oftenest, even a well-prepared mind guesses wrong. But the modicum of success of our guesses far exceeds that of sheer luck and seems born of attunement to nature by instincts developed or inherent, especially insofar as best guesses are optimally plausible and simple in the sense, said Peirce, of the facile and natural, as by Galileo's natural light of reason and as distinct from logical simplicity. Abduction is the most fertile but least secure mode of inference. Its general rationale is inductive, it succeeds often enough and, without it, there is no hope of sufficiently expediting inquiry, often multi-generational, toward new truths. 123. Coordinative method leads from abducing a plausible hypothesis to judging it for its testability. 23. And for how its trial would economize inquiry itself. 22. Peirce calls his pragmatism the logic of abduction. 124. His pragmatic maxim is, consider what effects that might conceivably have practical bearings you conceive the objects of your conception to have. Then, your conception of those effects is the whole of your conception of the object. 34. His pragmatism is a method of reducing conceptual confusions fruitfully by equating the meaning of any conception with the conceivable practical implications of its object's conceived effects, a method of experimental mental reflection hospitable to forming hypotheses and conducive to testing them. It favors efficiency. The hypothesis, being insecure, needs to have practical implications leading at least to mental tests and, in science, lending themselves to scientific tests. A simple but unlikely guess, if uncostly to test for falsity, may belong first in line for testing. A guess is intrinsically worth testing if it has instinctive plausibility or reasoned objective probability, while subjective likelihood, though reasoned, can be misleadingly seductive. Guesses can be chosen for trial strategically, for their caution, for which Peirce gave as an example the game of 20 questions, breadth, and in complexity. 125. One can hope to discover only that which time would reveal through a learner's sufficient experience anyway, so the point is to expedite it. The economy of research is what demands the leap, so to speak, of abduction and governs its art. 22. Deduction. 2 stages. Explication. Unclearly premised, but deductive, analysis of the hypothesis in order to render its parts as clear as possible. Demonstration, deductive argumentation, Euclidean in procedure. Explicit deduction of hypothesis's consequences as predictions, for induction to test, about evidence to be found. Corollarial or, if needed, theorematic. Induction. The long-run validity of the rule of induction is deducible from the principle, presuppositional to reasoning, in general. 34. That the real is only the object of the final opinion to which adequate investigation would lead. Wink with a frown. 126. Anything to which no such process would ever lead would not be real. Induction involving ongoing tests or observations follows a method which, sufficiently persisted in, will diminish its error below any predesignate degree. 3 stages. Classification. Unclearly premised, but inductive, classing of objects of experience under general ideas. Probation. Direct inductive argumentation. Crude, the enumeration of instances, or gradual, new estimate of the proportion of truth in the hypothesis after each test. Gradual induction is qualitative or quantitative. If qualitative, then dependent on weightings of qualities or characters. Wink with a frown. 127. If quantitative, then dependent on measurements, or on statistics, or on countings. Sentential induction, which, by inductive reasonings, appraises the different probations singly, then their combinations, then makes self-appraisal of these very appraisals themselves, and passes final judgment on the whole result. Invariant explanation. Model of DNA with David Deutsch, proponent of invariant scientific explanations, 2009. This section is transcluded from David Deutsch. Edit, History. In a 2009 TED Talk, Deutsch expounded a criterion for scientific explanation, which is to formulate invariants, state an explanation, publicly, so that it can be dated and verified by others later, that remains invariant, in the face of apparent change, new information, or unexpected conditions. 128. A bad explanation is easy to vary. 128, minute 11:22. The search for hard-to-vary explanations is the origin of all progress. 128, minute 15:05. That the truth consists of hard-to-vary assertions about reality is the most important fact about the physical world. 128, minute 16:15. Invariance as a fundamental aspect of a scientific account of reality had long been part of philosophy of science. For example, Friedel Weinert's book The Scientist as Philosopher, 2004, noted the presence of the theme in many writings from around 1900 onward, such as works by Henri Poincaré, 1902, Ernst Cassirer, 1920, Max Born, 1949 and 1953, Paul Dirac, 1958, Olivier Costa de Beauregard, 1966, Eugene Wigner, 1967, Lawrence Sklar, 1974, Michael Friedman, 1983, John D. Norton, 1992, Nicholas Maxwell, 1993, Alan Cook, 1994, Alastair Cameron Crombie, 1994, Margaret Morrison, 1995, Richard Feynman, 1997, Robert Nozick, 2001, and Tim Maudlin, 2002. 129. Communication and community. Frequently the scientific method is employed not only by a single person but also by several people cooperating directly or indirectly. Such cooperation can be regarded as an important element of a scientific community. Various standards of scientific methodology are used within such an environment. Peer review evaluation. Scientific journals use a process of peer review, in which scientists' manuscripts are submitted by editors of scientific journals to, usually 1 to 3, and usually anonymous, fellow scientists familiar with the field for evaluation. In certain journals, the journal itself selects the referees, while in others, especially journals that are extremely specialized, the manuscript author might recommend referees. The referees may or may not recommend publication, or they might recommend publication with suggested modifications, or sometimes, publication in another journal. This standard is practiced to various degrees by different journals and can have the effect of keeping the literature free of obvious errors and generally improve the quality of the material, especially in the journals that use the standard most rigorously. The peer review process can have limitations when considering research outside the conventional scientific paradigm. Problems of groupthink can interfere with open and fair deliberation of some new research. 130. Documentation and replication. Main article, reproducibility. Sometimes experimenters may make systematic errors during their experiments, veer from standard methods and practices, pathological science, for various reasons, or, in rare cases, deliberately report false results. Occasionally because of this other scientists might attempt to repeat the experiments to duplicate the results. Archiving. Researchers sometimes practice scientific data archiving, such as in compliance with the policies of government funding agencies and scientific journals. In these cases, detailed records of their experimental procedures, raw data, statistical analyses, and source code can be preserved to provide evidence of the methodology and practice of the procedure and assist in any potential future attempts to reproduce the result. These procedural records may also assist in the conception of new experiments to test the hypothesis, and may prove useful to engineers who might examine the potential practical applications of a discovery. Data sharing. When additional information is needed before a study can be reproduced, the author of the study might be asked to provide it. They might provide it, or if the author refuses to share data, appeals can be made to the journal editors who published the study or to the institution which funded the research. Limitations. Since a scientist cannot record everything that took place in an experiment, facts selected for their apparent relevance are reported. This may lead, unavoidably, to problems later if some supposedly irrelevant feature is questioned. For example, Heinrich Hertz did not report the size of the room used to test Maxwell's equations, which later turned out to account for a small deviation in the results. The problem is that parts of the theory itself need to be assumed to select and report the experimental conditions. The observations are hence sometimes described as being theory-laden. Science of complex systems. Science applied to complex systems can involve elements such as transdisciplinarity, systems theory, control theory, and scientific modeling. The Santa Fe Institute studies such systems. With a frown 78, Murray Gell-Mann interconnects these topics with message passing. 131, 20. Some biological systems, such those involved in proprioception, have been fruitfully modeled by engineering techniques. 132, 133. In general, the scientific method may be difficult to apply stringently to diverse, interconnected systems and large data sets. In particular, practices used within big data, such as predictive analytics, may be considered to be at odds with the scientific method. 134, as some of the data may have been stripped of the parameters which might be material in alternative hypotheses for an explanation, thus the stripped data would only serve to support the null hypothesis in the predictive analytics application. Fleck 1979, pages 38 to 50 notes a scientific discovery remains incomplete without considerations of the social practices that condition it. 135. Analytical philosophy. Philosophy of science looks at the underpinning logic of the scientific method, at what separates science from non-science, and the ethic that is implicit in science. There are basic assumptions, derived from philosophy by at least one prominent scientist, c. 136, that form the base of the scientific method, namely, that reality is objective and consistent, that humans have the capacity to perceive reality accurately, and that rational explanations exist for elements of the real world. 136. These assumptions from methodological naturalism form a basis on which science may be grounded. Logical positivist, empiricist, falsificationist, and other theories have criticized these assumptions and given alternative accounts of the logic of science, but each has also itself been criticized. Thomas Kuhn examined the history of science in his The Structure of Scientific Revolutions, and found that the actual method used by scientists differed dramatically from the then espoused method. His observations of science practice are essentially sociological and do not speak to how science is or can be practiced in other times and other cultures. Norwood Russell Hansen, Imre Lakatos and Thomas Kuhn have done extensive work on the theory-laden character of observation. Hansen, 1958, first coined the term for the idea that all observation is dependent on the conceptual framework of the observer, using the concept of gestalt to show how preconceptions can affect both observation and description. 137, he opens Chapter 1 with a discussion of the Golgi bodies and their initial rejection as an artifact of staining technique, and a discussion of Brahe and Kepler observing the dawn and seeing a different sunrise despite the same physiological phenomenon. Kuhn, 138, and Feyerabend, 139, acknowledge the pioneering significance of Hansen's work. Kuhn said, "Propose striking this paragraph as inconsistent with the article. The scientist generally has a theory in mind before designing and undertaking experiments to make empirical observations, and that the route from theory to measurement can almost never be traveled backward." For Kuhn, this implies that how theory is tested is dictated by the nature of the theory itself, which led Kuhn to argue that once it has been adopted by a profession, no theory is recognized to be testable by any quantitative tests that it has not already passed, revealing Kuhn's rationalist thinking style. 140. Postmodernism and Science Wars. Paul Feyerabend similarly examined the history of science, and was led to deny that science is genuinely a methodological process. In his book Against Method he argues that scientific progress is not the result of applying any particular method. In essence, he says that for any specific method or norm of science, one can find a historic episode where violating it has contributed to the progress of science. Thus, if believers in the scientific method wish to express a single universally valid rule, Feyerabend jokingly suggests, it should be anything goes. 141, however, this is uneconomic. Criticisms such as Feyerabend's led to the Strong Program, a radical approach to the sociology of science. The postmodernist critiques of science have themselves been the subject of intense controversy. This ongoing debate, known as the Science Wars, is the result of conflicting values and assumptions between the postmodernist and realist camps. Whereas postmodernists assert that scientific knowledge is simply another discourse, this term has special meaning in this context, and not representative of any form of fundamental truth, realists in the scientific community maintain that scientific knowledge does reveal real and fundamental truths about reality. Many books have been written by scientists which take on this problem and challenge the assertions of the postmodernists while defending science as a legitimate method of deriving truth. 142. Anthropology and Sociology. In Anthropology and Sociology, following the field research in an academic scientific laboratory by Latour and Woolgar, Karen Noor-Sedina has conducted a comparative study of two scientific fields, namely high-energy physics and molecular biology, to conclude that the epistemic practices and reasonings within both scientific communities are different enough to introduce the concept of epistemic cultures, in contradiction with the idea that a so-called scientific method is unique and a unifying concept. 143. Comparing epistemic cultures with Fleck 1935, Thought Collectives, Denkkollektiven Ensthung, und Entwicklung einer wissenschaftlichen Tatsache, Einführung in die Lehre vom Denkstil und Denkkollektiv. 144, Fleck 1979, page 27 recognizes that facts have lifetimes, flourishing only after incubation periods. His selected question for investigation, 1934, was how, then, did this empirical fact originate and in what does it consist? 145, but by Fleck 1979, page 27, the thought collectives within the respective fields will have to settle on common specialized terminology, publish their results and further intercommunicate with their colleagues using the common terminology, in order to progress. 146. C. Cognitive revolution, psychology and neuroscience. Relationship with mathematics. Science is the process of gathering, comparing, and evaluating proposed models against observables. A model can be a simulation, mathematical or chemical formula, or set of proposed steps. Science is like mathematics in that researchers in both disciplines try to distinguish what is known from what is unknown at each stage of discovery. Models, in both science and mathematics, need to be internally consistent and also ought to be falsifiable, capable of disproof. In mathematics, a statement need not yet be proved. At such a stage, that statement would be called a conjecture. But when a statement has attained mathematical proof, that statement gains a kind of immortality which is highly prized by mathematicians, and for which some mathematicians devote their lives. 147. Mathematical work and scientific work can inspire each other. 33. For example, the technical concept of time arose in science, and timelessness was a hallmark of a mathematical topic. But today, the Poincaré conjecture has been proved using time as a mathematical concept in which objects can flow, see Ricci flow. Nevertheless, the connection between mathematics and reality, and so science to the extent it describes reality, remains obscure. Eugene Wigner's paper, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, is a very well-known account of the issue from a Nobel Prize-winning physicist. In fact, some observers, including some well-known mathematicians such as Gregory Chaitin, and others such as Lakoff and Nunez, have suggested that mathematics is the result of practitioner bias and human limitation, including cultural ones, somewhat like the postmodernist view of science. George Polya's work on problem-solving, 148, the construction of mathematical proofs, and heuristic, 149, 150, show that the mathematical method and the scientific method differ in detail, while nevertheless resembling each other in using iterative or recursive steps. Mathematical method, scientific method. 1. Understanding characterization from experience and observation. 2. Analysis hypothesis, a proposed explanation. 3. Synthesis deduction, prediction from the hypothesis. 4. Review/extend test and experiment. In Polya's view, understanding involves restating unfamiliar definitions in your own words, resorting to geometrical figures, and questioning what we know and do not know already. Analysis, which Polya takes from Pappas, 151, involves free and heuristic construction of plausible arguments, working backward from the goal, and devising a plan for constructing the proof. Synthesis is the strict Euclidean exposition of step-by-step details, 152, of the proof. Review involves reconsidering and re-examining the result and the path taken to it. Building on Polya's work, Imre Lakatos argued that mathematicians actually use contradiction, criticism, and revision as principles for improving their work. 153, AC, in like manner to science, where truth is sought, but certainty is not found. In proofs and refutations, what Lakatos tried to establish was that no theorem of informal mathematics is final or perfect. This means that we should not think that a theorem is ultimately true, only that no counterexample has yet been found. Once a counterexample, i.e. an entity contradicting/not explained by the theorem is found, we adjust the theorem, possibly extending the domain of its validity. This is a continuous way our knowledge accumulates, through the logic and process of proofs and refutations. However, if axioms are given for a branch of mathematics, this creates a logical system. Wittgenstein 1921 Tractatus Logico-Philosophicus 5.13, Lakatos claimed that proofs from such a system were tautological, i.e. internally logically true, by rewriting forms, as shown by Poincaré, who demonstrated the technique of transforming tautologically true forms, viz. the Euler characteristic, into or out of forms from homology, 154, or more abstractly, from homological algebra, 155, 156, AC. Lakatos proposed an account of mathematical knowledge based on Polya's idea of heuristics. In Proofs and Refutations, Lakatos gave several basic rules for finding proofs and counterexamples to conjectures. He thought that mathematical thought experiments are a valid way to discover mathematical conjectures and proofs. 158. Gauss, when asked how he came about his theorems, once replied durch planmäßiges Tattenieren, through systematic palpable experimentation. 159. Relationship with statistics. When the scientific method employs statistics as a key part of its arsenal, there are mathematical and practical issues that can have a deleterious effect on the reliability of the output of scientific methods. This is described in a popular 2005 scientific paper, Why Most Published Research Findings Are False by John Ioannidis, which is considered foundational to the field of metascience. 160. Much research in metascience seeks to identify poor use of statistics and improve its use. Add M. See pre-registration, science, #rationale. The particular points raised are statistical. The smaller the studies conducted in a scientific field, the less likely the research findings are to be true, and the greater the flexibility in designs, definitions, outcomes, and analytical modes in a scientific field, the less likely the research findings are to be true, and economical, the greater the financial and other interests and prejudices in a scientific field, the less likely the research findings are to be true, and the hotter a scientific field, with more scientific teams involved, the less likely the research findings are to be true. Hence, most research findings are false for most research designs and for most fields, and as shown, the majority of modern biomedical research is operating in areas with very low pre- and post-study probability for true findings. However, nevertheless, most new discoveries will continue to stem from hypothesis-generating research with low or very low pre-study odds, which means that new discoveries will come from research that, when that research started, had low or very low odds, a low or very low chance, of succeeding. Hence, if the scientific method is used to expand the frontiers of knowledge, research into areas that are outside the mainstream will yield the newest discoveries. C. Expected value of sample information, false positives and false negatives, test statistic, and type 1 and type 2 errors. Role of chance in discovery. Main article, Role of chance in scientific discoveries. Somewhere between 33% and 50% of all scientific discoveries are estimated to have been stumbled upon, rather than sought out. This may explain why scientists so often express that they were lucky. 161. Louis Pasteur is credited with the famous saying that luck favors the prepared mind, but some psychologists have begun to study what it means to be prepared for luck in the scientific context. Research is showing that scientists are taught various heuristics that tend to harness chance and the unexpected. 161, 162. This is what Nassim Nicholas Taleb calls antifragility. While some systems of investigation are fragile in the face of human error, human bias, and randomness, the scientific method is more than resistant or tough. It actually benefits from such randomness in many ways. It is antifragile. Taleb believes that the more antifragile the system, the more it will flourish in the real world. 52. Psychologist Kevin Dunbar says the process of discovery often starts with researchers finding bugs in their experiments. These unexpected results lead researchers to try to fix what they think is an error in their method. Eventually, the researcher decides the error is too persistent and systematic to be a coincidence. The highly controlled, cautious, and curious aspects of the scientific method are thus what make it well suited for identifying such persistent systematic errors. At this point, the researcher will begin to think of theoretical explanations for the error, often seeking the help of colleagues across different domains of expertise. 161, 162. See also. Armchair theorizing. Contingency, status of propositions that are neither always true nor always false. Empirical limits in science, idea that knowledge comes only/mainly from sensory experience. Evidence-based practices, pragmatic methodology. Fuzzy logic, system for reasoning about vagueness. Information theory, scientific study of digital information. Logic, study of correct reasoning. Historical method, techniques used by historians. Philosophical methodology, study of the methods of philosophy. Scholarly method, body of principles and practices used by scholars and academics to make their claims. Methodology, study of research methods. Metascience, scientific study of science. Operationalization, part of the process of research design. Quantitative research, all procedures for the numerical representation of empirical facts. Rhetoric of Science. Royal Commission on Animal Magnetism, 1784. French scientific bodies. Scientific law, statement based on repeated empirical observations that describes some natural phenomenon. Social research, research conducted by social scientists. Strong inference, philosophy of science concept emphasizing the need for alternative hypotheses. Testability, extent to which truthness or falseness of a hypothesis/declaration can be tested. Unsupervised learning, a paradigm in machine learning. Verificationism, philosophical doctrine. Problems and issues. Descriptive science, used to describe characteristics of a phenomenon being studied. Design science, a systematic form of designing. Holism in science, approach to research that emphasizes the study of complex systems. Junk science, scientific data considered to be spurious. List of cognitive biases, systematic patterns of deviation from norm or rationality in judgment. Normative science, aspect of science. Philosophical skepticism, philosophical views that question the possibility of knowledge or certainty. Poverty of the stimulus, linguistic argument. Problem of induction, question of whether inductive reasoning leads to definitive knowledge. Pseudoscience, unscientific claims wrongly presented as scientific. Reference class problem, issue when estimating a probability. Replication crisis, observed inability to reproduce scientific studies. Skeptical hypotheses, philosophical views that question the possibility of knowledge or certainty. Underdetermination, idea in the philosophy of science. History, philosophy, sociology. Baconian method, investigative process. Epistemology, branch of philosophy concerning knowledge. Epistemic truth, attempts to analyze the concept of truth. Mertonian norms, philosophical ideals for the practice of science. Normal science, regular work of scientists. Post-normal science, approach to the use of science on urgent issues involving uncertainty in facts and moral values. Science studies, research area analyzing scientific expertise. Timeline of the history of scientific method.